Good morning, Astronomy 1010. Welcome to our second week of lecture. Today we're going to do homework number 2, which is going to be a bit of a wild ride, lots of tricky questions. We're going to do lecture number 3, where we're going to learn about timekeeping and, well, a whole mishmash of things related to astronomy and maybe even a little bit about the history of astronomy. And then we're going to have a lab, a kind of quirky lab on eclipse prediction, which I like a lot. And we're going to do all that today. So let's get into it. Let's get into homework number 2. Oh, announcements. On Monday night, I graded your homeworks. And for the most part, they were awesome because everyone did exactly what I wanted them to do. And it was nice and it was neat and it was tidy. And that's when things work out well. A couple of people got creative, by which I mean they attempted to do the homework like totally on their own, and it seems like without even watching lecture. Otherwise, I can't really imagine why they would do that. That turned out to not work out so well. So I graded it appropriately based on the, how much it made me happy and how much it didn't. I would probably prefer if you guys just watch the video and just do what I say. And that's going to make things better for both of us. Also, these homeworks are going to become really nice study guides for the exam. And I worry that, well, it takes a long time to watch these lectures. And I know that. It takes a long time to give these lectures. But you have to do it because it's like how classes work and stuff. So I don't think any of you guys in my live show here had an issue, but let me I meant to do this before class started here, but I was distracted. Let me go to summer 2021 and just do a quick peek because it was now 2 days ago. And let's see. No, you guys all did it correctly, which is good. So we've got Jeff, Nicole, and Nina, and some people in the background. And yeah, you guys were great. So that's wonderful. But if you're watching later on and you were one of the people that I had to grade a little harshly, you should probably get in touch with me so we could talk. There are many ways to contact me. I put them on the syllabus. Reach out. Okay, let's take a look and share screen over towards our homework. And let's grab those problem numbers. They're from chapter S1, special chapter S1 here. Here's homework number 2. If you guys are willing to, Jeff, Nicole, Nina, right-click and open this up in a new tab so you have the questions there. I might want you guys to read me some of those questions. Okay, 38, 41, 47, 51, 53. So let's set up our papers the way I like it. Let's focus on me. Let me change the lighting a bit. All right, put your name on that paper. Put Astronomy 1010 on that paper. This is homework number 2. We're working with special chapter S1. The questions are 38. Help me, Nicole. What else are they? You're muted.
38, 41, 47, 51, and then 53, A, B, and C.
All right. I suspect we're going to have to do 53 during the lecture, but we'll see. This homework, I did a similar one yesterday, and it took a while. The first question's a tough one, and it's especially tough because we didn't cover the subject. So you're going to love this. Let me start by giving you a little bit of background. Okay, In my slideshow, and I was just about to get to this when we ended class yesterday. I was so close. I thought I was going to make it. I wanted to talk to you guys about timekeeping and the fact that there are different types of day. So when someone asks you how long is a day, your first thought is, I know how long a day is. It's 24 hours. And in a sense, you're right, provided you're talking about a solar day. A solar day is what we measure when we keep track of the passage of time using the sun as a reference point. And as human beings who descended from human beings who were part of an agricultural society, I don't know if we're so agricultural anymore. Some of us are, but not too many. We are concerned with the motion of the sun because the sun brings light so we can see and do things. And it's especially important for growing plants. So when you keep track of the passage of time using the sun, I suppose one of the earliest methods of doing this would have been to use a sundial, right? And somewhere in here, I've got a picture of a sundial. Let me see if I can find one. There we go. Okay, so here's a cool looking sundial. It's got a dais where you mark out all of the hours. And this stick that you see here has a funny name. It's called a gnomon, okay? Gnomon, something like that. It's a gnomon. And the gnomon's job is to cast a shadow based on the motion of the sun, and the shadow moves across the different hour markings on the dais. Usually the gnomon points towards the North Star, Polaris, and that way this edge here is kind of pointed south. And let's think about how the sun is moving through the sky a little bit. This is going to be part of my lecture today, so I shouldn't steal all of my fire. But I have a picture here. That's what I wanted. Here's the sun moving through the local sky. In our sky, the sun sort of does something like this. It moves vaguely east to west, angled towards the south. And we can talk more about that today. It turns out that 24 hours is not the true axis spin of Earth. You would think that Earth takes exactly 24 hours to spin on its axis, but in fact, Earth spins on its axis every 23 hours and 56 seconds. And that means there's two different ways of keeping track of a day. There's a solar day where you keep track of the motion of the sun, and there's a sidereal day where you keep track of the motions of the stars. This little picture tries to show how it works, and I'm going to sort of add some extra Earths in here using my drawing tool. So let me see if I can put in a couple more Earths. During the course of a 24-hour day, Earth is moving a little bit around the sun on its orbit. And so the Earth is doing a two-step motion where it's spinning on its axis and it's also going around the sun in its yearly orbit. Because there's 360 degrees in a circle and there's about 365 days in a year, 360 and 365 are so close to each other that the Earth moves roughly 1 degree each day in its orbit, which isn't a lot. It's a small motion, but it's enough to change the geometry of the situation. Let's imagine that you're an observer standing on Earth and that your meridian, the sort of north-south line, is pointed here towards the sun. So there's your meridian. And that means you're about here on Earth. This is where, say, Rhode Island is. When an observer's meridian points towards the sun, that makes it 12 o'clock noon in your local time. For instance, if you had a sundial, let's go back to my sundial here. When the sun reaches its highest point, it crosses the meridian here. So there you can see your meridian, right? And that's when the shadow that the stick makes will be the shortest. It's going to point, well, here to noon. Now let's imagine that Earth starts its spin and a day starts going past. Damn it, I lost my little Earths here. I can already tell I'm off to a sloppy start to this day. Ooh, nope, let's not do that. Let's do blue. Okay, So let me draw in a few more Earths so you can watch Earth spinning on its axis. And what I'm going to do is I'm going to try to move some of these guys. Let's move him here. Let's move him here. Move him here. Okay. During the course of a day, as Earth spins, let's see, which direction does Earth spin as seen from above? Do you guys remember?
Counterclockwise.
Counterclockwise. Good. So if my first arrow is pointed towards noon in this direction, then as I spin against the clock, my next arrow, my head will point down here. And then as I keep spinning, my arrow is going to point over here because I'm sort of going around in this direction. That's counterclockwise, right? Can everyone see what I'm doing here? I'm drawing the observer's meridian arrow. And then the observer is going to point up here. And at last, the Earth will complete a true 360-degree spin. And now the arrow will point in the direction of this blue arrow that I just drew. At this point, at this moment right here, the Earth has completed a 360-degree rotation. And that takes 23 hours and 56 minutes. However, Earth is moved out of the direction of the sun, so it's no longer a local observer's noon. Notice that the arrow is pointing here for your meridian, and the sun is not quite at your meridian. It needs to spin and rotate a little bit more. Or rather, what needs to happen is Earth needs to keep moving and spinning to get the observer's meridian pointed back towards the sun. Now, this is something you've never thought about before, and most people don't think about it because they're not busy tracking the motion of stars as they go around the sky. They're more busy tracking the sun. So the time that you keep when I start this class late, for instance, is our watches keep solar time. We want our days and nights to be synchronized to the clock. It is possible, however, to keep time by stars. And interestingly enough, although this second arrow no longer points back towards the sun, it will point towards the same star on the celestial sphere. Now, this one you're going to have to try to hear me out on. Let's imagine that this first arrow here points towards a famous star. And let's say that star is, I don't know, Arcturus, okay? After Earth completes a 360 spin, this arrow will also point towards Arcturus. And according to this diagram, that looks a little weird. How can Arcturus be both here and here? Does anyone know how that's possible?
Is it because it's so far away that it's angular? It's going to be in the same general spot in the sky.
That's a pretty.
The Earth is only moving a little.
That's a pretty damn good way to put it. The sky is so infinite. The stars are so much farther away than the sun that anything that points in a parallel line will point towards the same star. And Jeff, we can almost kind of demonstrate that a bit with my whiteboard here. If you were thinking about trying to draw the stars, so let's put a star. Arcturus is yellow. Can I do this? Let's put a star over here, okay? Compared to the distance of the stars, the orbit of Earth is truly a pitifully small thing. So let's use yellow for the sun. So here's the sun. Okay, that's pretty tiny. And I'm going to try to get it sort of lined up with the star here a little bit. Wow, that's so tiny, I can't even, I intended to do that. The orbit of Earth, which I'll draw in black, or maybe I'll do it in blue. The orbit of Earth is a circle that's really tiny, really small, and really far away of some distant star. Now, this doesn't even do justice to the extreme difference between the orbit of Earth and the star. I'd have to actually draw it so small that we couldn't see it. But now you're starting to see, and Jeff kind of said it properly, that it doesn't matter if the Earth is there in its orbit, or there in its orbit, or there in its orbit. As the distance to the stars gets farther and farther away, any arrow that points towards the left is going to point towards this star. So Jeff understood it, but I wanted to kind of try to demonstrate it. To draw this really to scale, I'd have to draw that circle even smaller, so small that it would be tough to show the geometry all at the same time. That's right. So there's a solar day and there's a sidereal day. Sidereal means with respect to the stars. Let's now read the question. Honestly, I'm probably going to have to give a spiel about that during today's lecture as well, but now we can answer the first question. So Nina, why don't you read it out to us?
Sure. 38, yes? Okay.
Yeah.
Opposite rotation. Suppose Earth rotated in a direction opposite to its orbital direction. That is, suppose it rotated clockwise, as seen from above the North Pole, but orbited counterclockwise. Would the solar day still be longer than this sidereal day? Explain.
Okay. Why don't we try to draw this diagram out, kind of the way I did on my whiteboard. Okay. So this is S1 number 38. And I think the title is something like Solar versus Sidereal Day. Or it's opposite rotation, actually.
Opposite rotation.
Sorry. Okay. Okay. So what we're going to do is we're going to draw the sun over here on the left. And I wish I had like a small circle maker. This Frisbee is too big. Let me see if I can get a coffee lid really quick. Okay, here's a lid to some breadcrumbs. This ought to work. All right, so let's draw a few Earths here. Actually, I'm going to have to lower my sun. I'm going to need a little headroom here. So here's the sun. Oh, I got to save this thing. And now let's draw the Earth over here. Not really to scale because I don't have that luxury if you're going to be able to see it. And I'm going to start with my first Earth. Just like we saw in the slideshow, with a local observer whose meridian is pointing towards the sun. That means the local observer at that arrow is going to be at 12 noon because the sun will be overhead. And what I'm going to do is, remember, in this problem, the orbit of Earth around the sun is still counterclockwise. So that's normal. But now the Earth's spin, I believe, has been reversed to clockwise, which is not normal, right? So if I'm going to orbit around the sun, I should still be headed in a counterclockwise direction. I'm going to draw 1, 2. It's kind of an art to making this drawing here. 1, 2, 3. Oh. See, I didn't really give myself enough room. All right, I'll cheat. 4, 5 Earths. This is actually not my finest work here. I probably should have made smaller circles is what I should have done. Actually, I'm going to attempt to freehand it. 1, 2, 3, 4, 5. The circles aren't as good, but my orbit is a little better here, okay? Okay, let's draw some arrows in. I want to show the observer's meridian rotating with the spin of Earth. Right now I'm pointed towards the, well, it's pointed to noon, but if you think of this as a clock, that's like the 9 o'clock hand. Where should the next arrow point? Am I making any sense or am I talking gibberish? So students, my goal is to demonstrate the spin of Earth by showing an arrow rotating around. Where do you think I should draw our next arrow?
If it's spinning counterclockwise? Normal of it?
Orbit is counterclockwise. The spin is clockwise.
Oh, gotcha.
Sorry, I had a fierce thirst there. So am I making any sense? Do you guys, huh?
3 o'clock, 1 o'clock.
Well, right now, oh, I see. Okay. So which direction should I point next, Jeff? I'm currently pointing here.
To the right.
To the right.
Well, my right. 3 o'clock clockwise.
So like this?
Yes.
Is that what you're trying to say? Okay. I agree with you. Let me actually, so that's where my next arrow should point. And I should keep going kind of in quarters, right, Jeff? The next arrow should point like so. The next arrow should point down. Now, the next arrow you'd think would point back to the left. However, notice that in between pointing down and in between pointing to the left, as the arrow rotates, there'll be an arrow that points towards the sun. So you can see here, we're spinning clockwise, but our orbit is counterclockwise. Let's label these 1, 2, 3, 4, 5. Let's have a test. Jeff, maybe you know the answer. One of these represents the solar day, and one of these represents the sidereal day. Can you tell me which number represents which?
So 5 is the solar day and 4 is the sidereal? No?
So,
Oh, I'm sorry. Yeah. So 3?
hold on. We didn't really get a proper lecture on this. We just kind of got thrown into the Shark Tank here. That's not fair. But the basic gist is that the solar day is basically the time for the sun to orbit the sky, whereas the sidereal day is the time for a star to orbit the sky. Sidereal in Latin means with respect to stars. So which number represents the time it takes from this start point for the sun to return to the same place in the sky? In other words, which is our solar day?
Number 4?
That's right. Now you got it, Jeff. How did you know number 4 was your solar day?
Because after one full rotation of the Earth, it's facing the sun again. It's facing the same
Right, but don't say one full rotation of Earth. Has Earth completed a full 360-degree rotation?
No, it hasn't.
Right. So what we want to restrict ourselves is saying is that's the time it takes the sun to come back to the position.
Okay,
of the
gotcha.
sky. So this is our solar day. And which would represent the sidereal day? Is that obvious or is that tricky?
5?
Nina?
2?
Not 2.
Okay.
If the observer's meridian's pointed to the left, at 2, Earth has only rotated 180 degrees. It's kind of spun like that, but you will not be pointing towards the same star again. Because if there's a star over here on the left, now your meridian is pointed to the right,
Yeah.
right? Here's a
Is it
hint.
5?
Yes,
5.
Nicole. How did you know 5 is the sidereal day?
Because it's pointed outwards towards the stars.
Yeah. Another way I like to think of it is that a sidereal day represents a true 360-degree spin. And it should be clear to everyone that number 5 constitutes a true 360-degree spin. Okay. This is the setup that they are proposing in number S138. However, you guys got so lost in the sauce, I think it would be a good idea for Nina to read the question again. And now let's see if we can answer it.
Opposite rotation. Suppose Earth rotated in a direction opposite to its orbital direction. That is, suppose it rotated clockwise, as seen from above the North Pole, but orbited counterclockwise. Would the solar day still be longer than the sidereal day? Explain.
Okay. So what do you guys think? Would the solar day still be longer than the sidereal day if Earth were to spin in the opposite direction? Does this diagram explain the answer? I thought it would, but sometimes I have wishful thinking. Do you have a guess or are we lost?
The same.
The same. Well, let's look at the normal situation. In the normal situation, Earth spins in such a way, let's get my arrow tool. The arrow is actually rotating counterclockwise, right? So as Earth goes around the sun, it points in this direction, and then it's got to rotate an extra 4 minutes to point back to the sun. In real reality, is the solar day longer or shorter than the sidereal day?
Shorter.
No, look, you can see it longer. 24 hours is greater than 23 hours and 56 minutes, Nicole.
Professor, is that different depending on where you are at the Earth? I mean, if you're near the pole,
No.
wouldn't your day?
Yeah, but only at the North Pole. Well, a little bit, but who cares about that? Not many people live at the poles, which is true, right?
Just curious, because I'm picturing, standing on the equator and doing, the sun doing one rotation over as opposed to.
This is the same whether you're on the equator and all the way up to maybe the Arctic Circle.
Okay.
So this will get messed up if you are at the poles. You have a point, Jeff, but I don't think we should get distracted by that, because for the vast numbers of people on Earth, unless you're a polar bear, or I think once you get up to a certain latitude, even the polar bears say, fuck this, So at the North Pole, the day is the same length as a year, so you have a point. So it does get messed up, but not many people live at the pole. So in general, that's not an issue. And this does work the same whether you're at Rhode Island's latitude or if you're at the equator. But first, I need to make sure you guys can answer some basic questions. I just asked which is longer, the solar day or the sidereal day, and you guys got it wrong. So that means something's not clicking here, right? The sidereal day is the true 360-degree spin of Earth. And if you can see the direction of my arrow here, if you start here, you're going to complete a 360-degree rotation before you point back to the sun, right? This question is asking, is the solar day still longer than the sidereal day? Jeff suggested it was the same, but I think our drawing tells a very different story. What does our drawing show?
The sidereal day is longer?
Yeah. When Earth is spinning, if Earth for some crazy reason were to spin clockwise, an observer's meridian would have to rotate back to the sun before it completed a 360-degree spin. Does the sidereal day change if you know, we're not changing the rate Earth spins. The rate that Earth spins is staying the same. And that suggests to me that the sidereal day should still stay the same. In other words, the true 360-degree spin of Earth should remain 23 hours and 56 minutes. Take a guess. How long do you think the solar day would be in this configuration?
Like 20 hours?
Not 20 hours. It's not going to be different by 3 hours.
So I'm not sure.
Like, Nina,
Yeah.
look at the normal configuration.
Okay.
What's the difference between the sidereal day and the solar day? What's the time difference?
4 minutes.
About 4 minutes. Forget about this, okay?
Okay.
It's 4 minutes from there to there. And that's because Earth has to spin an extra 4 minutes. Earth basically rotates 1 degree every 4 minutes.
Yeah.
So by analogy, the solar day should now be how long?
If the solar day is shorter than the sidereal day,
Yeah.
like 23 hours and 50 minutes or 52
Not
minutes?
50, but
52?
that's right. In this configuration, the solar day would be 4 minutes shorter than the sidereal day.
Okay.
All right, it's time to write our answer down. Let me get my stool out so I can leave this drawing up. I knew this question was going to suck because you didn't have time to digest this information. If the Earth were to spin clockwise while continuing to orbit counterclockwise, then the solar day would no longer, all right, let's be careful how I say this here. The solar day would not be longer than the sidereal day. In fact, it would be 4 minutes shorter at 23 hours and 52 minutes. Okay, the diagram, as far as I'm concerned, explains why, but we have to answer why in words. That can be difficult. Do any of you want to try to explain what's going on here before I give you my interpretation? Who can explain why the solar day is shorter than the sidereal day based on that picture? This is a useful exercise. What made the solar day shorter this time?
The spin.
Something about the spin, but we need more than that, Nina. Is this too much for you guys? I just want someone to try to explain this to me. I'm not sure. I'm not even sure if you understand this. I don't even know if you know what your name is. You know, you guys could just be sitting there going,
Is it something like, if the Earth rotated in clockwise, the sidereal day would well, not finish, but the Earth would make a full 360 rotation sooner than the solar day because
but that's not what happened, Nina.
no. Okay.
Look, the sidereal day did not complete before the solar day.
Oh, you're right. Yes.
Right?
Oh, okay.
See how hard this is? I want you to try. I know this is hard. That's why I'm asking you to do it. So the solar day completes before the sidereal day. The sidereal day does not change. It's still the true 360 spin of Earth. It's the solar day that's shorter. So what happened with the solar day? It's all about that fucking arrow. What's up with the arrow?
Yeah, so when it's spinning clockwise with the orbit, it takes less distance to point back at the sun.
I don't say distance.
Well, less.
This is about angles more than distance, but.
So it's less of an angle to point back at the sun when it's spinning counterclockwise.
Now, Jeff, you're doing good.
Yeah.
It takes less time for it to point back to the sun. What is it? What is it?
That's the zenith, the observer,
All right, you're getting warmer. The observer's location.
The observer's location.
I'd like to say zenith. That would be cute, wouldn't it? Except it's not really the zenith because the sun doesn't really hit
not directly
the zenith.
overhead. Okay.
It's the observers. It's not the zenith. If only I had a cool vocabulary word to describe this line that runs from north to south.
Meridian?
The meridian.
All right.
It is the meridian. A local observer's meridian will point back to the sun before the meridian completes a true 360 spin. That's how we say this. Let's write that down. You eventually got there. I'm impressed. This is because a local observer's meridian, there's how we use that term. The local observer's meridian will point back to the sun and if we want, we can get technical and include the fact that it's 1 degree. 1 degree is equal to about 4 minutes. We'll point back to the sun 1 degree sooner. Than it completes a full 360 degree spin. That's a nice way to say that. Sorry about the handwriting. 1 degree sooner sounds weird, but it's actually accurate. In astronomy, the spin of Earth is time. You guys got all that? Okay, well, that was fun. The rest of these ought to be even funner, okay? Well, it would have been better if we'd had time to talk about it last class. All right. Nicole, you're up. Read chapter S141. What's the title?
It is Fundamentals of Your Local Sky.
Okay.
And it says, well, it's written out in like letters. So it says A, where is the north
Wait.
or
You
south?
skipped a part. You need to read everything. You missed something.
Huh?
I'm pretty sure you did. Are there 2 pages here? Okay. Do you understand what you, all right, let me show you what you missed, Nicole. You start off by saying fundamentals of your local sky, then you hopped over all that, and then you went to A. That's my
Okay.
issue. Okay?
So fundamentals of your local sky, answer each of the following for your latitude.
All right, stop. What's the latitude that we're at? What is the latitude of Providence, Rhode Island? I gave that to you last class. Or look at your phone's compass app. I don't know.
Latitude is 42 degrees north.
Good. That should be in your lecture notes from last class. Okay, Nicole, now you can read A and just stop after A.
Okay. Where is north or south celestial pole in your sky?
Since we're in the northern hemisphere, we will see the north celestial pole, not the south celestial pole. You got to go to Argentina to see the south celestial pole. Okay, how are we going to answer this question? This actually is something that you've been trained on, in a way. Last class, you learned a whole bunch of useful coordinates to describe the location of things in your sky. I think I had to give you a hint because I'm nice like that. Oh man, this is the crappy slideshow. I really need to do a thing. I've been dying to fix this for years. I need the best picture. One of the best pictures in this whole slideshow is right here. And I need to update it here. There we go. 66. I like that. All right, this is a diagram of your local sky. You drew this last class. Where is the north celestial pole on this diagram?
The red arrow.
Very good. This is the north celestial pole. That's where it is on your sky. NCP. This question wants us to describe that point on our sky for Providence, Rhode Island's latitude. Can you do it? Actually, there's an exercise that we're going to do at the beginning of class that would have helped here. Which coordinate system do you think we should use? You learned 2 coordinate systems last time.
Degrees.
Well, both involve degrees. Degrees is a unit. I'm asking you about like a coordinate system.
Oh, the alt-as maybe.
Alt-as, that's right. Jeff, yes. We want to use the horizon system. I want to describe this point using an altitude, that's degrees up, and I want an azimuth, which is degrees along the horizon. Okay. Let's draw a little picture. Okay, you guys draw this with me. Let's draw a two-dimensional local sky. Make a quick dome with a protractor or something. Put an observer in the center. Draw the observer's zenith. Now we will draw the north celestial pole and perpendicular to that we'll draw the celestial equator. This is a two-dimensional local sky. We'll make a better version of this in class today. Let's review geographical coordinates. What is the definition of latitude? Let's read it from our books.
The latitude is the degrees north or south of the equator.
So in Rhode Island, it's telling us that the angle between the equator and us is 42 degrees, okay? The equator points towards the celestial equator. The North Pole points towards the North Celestial Pole. Let me see if I can make this smaller. And your head points towards the zenith. So the idea is, let's draw a picture so you can see this. Let's draw Earth with the same orientation. North Pole, equator, and here's you. Your latitude is the angle between you, your feet, and the equator. But the equator points towards the celestial equator, and your head points towards the zenith. So that means this angle here is also your latitude, 42 degrees. Okay. If there's a 90-degree angle between the equator and the North Pole, what should this angle be?
48 degrees north.
If there's a 90-degree angle between the zenith and the horizon, what should that angle be?
$42 degrees.
And what angle should that be over here?
48.
Good. Now, Jeff suggested that we should use the horizon system. He didn't call it that, but that's what he was talking about when he said Alt-As. The horizon system uses an altitude and an azimuth. And we want both to describe the location of the North Celestial Pole. Let's review the definitions, because I suspect you guys have forgotten the definitions of those things. What's the definition of altitude? Someone regurgitate it for me.
Degrees above the nearest horizon.
Okay. What is the nearest horizon to the North Celestial Pole? Sorry, Jeff?
Celestial equator? Or the equator?
Nope. I asked you, what is the closest horizon point? The celestial equator is not the same as the horizon.
So it's going to be your zenith?
No, okay. I think you guys forgot what horizon means. Let's look at the 3D local sky. Where's the horizon in this picture?
The green area?
The green area is the grass. That's the ground. That's not the same thing technically as the horizon.
Oh, okay.
I mean, kind of, Nina, but you have to do better than that. That's not acceptable for me. Saying all of this green stuff is the horizon is not okay.
Is it the circle, the base of the?
The circle around the green stuff is okay.
Yeah.
This is your horizon, right?
Yeah.
All right, that's fine. What is the closest point on the horizon to the North Celestial Pole? I wish I could let you guys draw on this thing, but I think they took that away from me. Can you draw on this? Try to draw on this. Take a mouse, try to draw. Can you draw?
No.
I used to be able to let students do that. Disable no, you should be able to do this. Hit the little draw tool. Do you not have a little, I don't know how to show this to you. You don't have a little annotate tool?
No.
Wow, this sucks. Share screen. I'm just trying to see if I can. You guys can't draw on this thing. You don't have an annotate tool. All right, then you're gonna have to describe it to me. I don't know how else to, this question, all right, the problem is we're having a failure to communicate here. The question I'm asking makes a lot of sense to me. I'm starting to think that the question I'm asking doesn't make any sense to you guys, and I don't know how to fix it. I need your help. I know that this is the North Celestial Pole. I want you guys to tell me what is the closest point on the horizon to the blue dot. And you guys can't do that.
North?
That makes, pardon?
North?
The northern horizon is the correct answer. In other words, right here. That's the closest point on the horizon to there. Thank you. Okay, now you understand me. Okay, so what's the definition of altitude again?
Degrees above or below the horizon.
Degrees above the nearest horizon. So how many degrees above the nearest horizon is the North Celestial Pole?
45 degrees.
Nope.
42.
42 degrees.
42, I'm sorry. That makes sense.
Therefore, your altitude is 42 degrees. What about your azimuth? Let's review the definition of azimuth. What is the azimuth of the north? Pardon?
Degrees along the horizon clockwise from north.
And that means you start here and then you move in that direction until you get to the closest point on the horizon.
Yeah.
So, can you tell me the azimuth?
0 degrees.
That's right, because your closest point on the horizon is north. You don't have to swivel at all along this disk. Okay? It's 0 degrees or north. Azimuth is the same thing as direction. So we could say 0 degrees or north. All right. This is going to be rough. North Celestial Pole. All right. Question B. Nina, I think you were the reader.
Sorry. Describe the meridian in your sky, specifying at least 3 distinct points along it, such as the points at which it meets your horizon and its highest point.
The meridian is an arc. That means we're going to need 3 points to describe it. I refer to these points as the rise, the reach, and the set. Each point, rise, reach, and set, is going to have an altitude and an azimuth. So we're going to need sort of 6 numbers here to do this right. My freehand art skills aren't so great. So let's look up the definition of meridian from last class, from last week. Where's the meridian? You can tell me or you can regurgitate the definition, but you have to do one of those 2 things.
The meridian is the arc that rises due north, reaches the zenith, and sets due south.
That's the meridian.
Yeah.
Okay. So I would say the 3 points then are, this is where it rises, that's the highest it reaches, and that's where it sets. So I need you guys to give me the altitude and azimuth of those 3 blue dots. Let's start with the one on the left. I need the altitude and azimuth of that point. You can give me one or both of them.
The azimuth is 0 or north.
Correct. You know that because you just did that. What's the altitude?
$42? No.
No. An altitude is degrees above the horizon. An altitude of 40 degrees would point up like that.
Yeah. Are we doing?
You're pointing there.
Oh, okay. Sorry. Then 0?
That's right. It's on the horizon, so its altitude is 0. Very good. Now we'll do the reach. That's the reach point. I need an altitude and an azimuth. Let's start with altitude.
90 degrees.
That's right, because if you go up, that's a 90-degree angle. What about the azimuth? This is trickier. The azimuth swivels along the horizon clockwise until you find the point on the horizon that is closest to your thing.
180.
But I don't think south is any closer to that point than north or east or west. One of the tricky things about being at the so-called zenith is that all points on the horizon are equidistant from the zenith, right? Can you see that? So what's kind of messed up about the azimuth is there is no point along the horizon that's closest to the zenith. And therefore the azimuth is undefined. It breaks down at the zenith, which is kind of tricky. So the reach is 90 degrees. The azimuth is weirdly undefined, but if we want, we can also mention that it's at the zenith, which is a unique point on the sky. Let's see if you guys are getting any better at this. I need the altitude and azimuth of the set point there. Give me the altitude and azimuth of that point.
Is the altitude 0?
The altitude 0, the azimuth.
0 or south?
South is not 0 in azimuth. What's the definition of azimuth, Nicole?
Degrees along the horizon measured clockwise from north.
So that's not 0, because if you start at north, Nicole, look at my arrow. You're actually swiveling more than 0 degrees to get to that point. How many degrees are you swiveling?
180?
That's the azimuth. 180 is south, okay? So the south part was correct. It was the 0 part that so the altitude is 0 degrees. The azimuth is 180 degrees or south. That's how we describe an arc through our sky: the rise, the reach, the set. Okay, Nina, or I'm sorry, Nicole, whoever was reading, what's part C?
Describe the celestial equator in your sky, specifying at least 3 distinct points along it.
Okay, we are going to reuse this diagram here, or this table, remake this table. I'm going to back the reach up a little bit. The celestial equator is also an arc, so it's going to have a rise, a reach, and a set. The celestial equator is the red arc that you see. And I believe the best points to describe are this point, the rise, this point, the reach, and that point, the set. Let's start with the rise. I need an altitude and an azimuth. Shout at me if you can do that. Actually, stare in befuddlement at the diagram while I fill my glass with ice water, because I'm very thirsty.
Did he say west was the reach or the rise?
You know, I was happy when I could hear you guys chatting with each other, but it seems to have petered out. You're missing the experience of a problem set here. Like, imagine doing this without your professor. That's what astronomy school is like. You go into a room with all the people in your class, and you sit there going, what? What the fuck is it asking? What am I supposed to do? And then you all sit there and bash your head in the wall until somebody has a eureka moment. And then you get 1 more hour of sleep that night because you just answered another question. Anyways,
Did
I
you say
digress.
west was the rise?
Well, either direction could be the rise, but why don't we make it astronomy related? Do stars rise in the west and set in the east?
No. Yes. No.
You need to watch Game of Thrones, man. Remember when Khaleesi says, I'm not going to stop loving you, Khal Drogo, until the sun rises in the west and sets in the east? That's supposed to sound fucked up. Things don't rise in the west. They rise in the east.
Then no.
Homework assignment. Watch Game of Thrones. Okay. No, Nina, I'm playing with you here. Things everything rises in the east and sets in the west, including the sun, the moon, stars, and everything else. That's because the earth is spinning eastward, right? Okay.
So we're doing east as the rise.
That would be my choice. If you want to be a total fucking weirdo, that's okay. If you want to rise in the west, it was cool when Khaleesi said it, you know. I don't know. It doesn't matter. Let's start with east as a rise point. Yeah.
Is it 66.5?
Whoa. Listen, we got to talk to each other in a reasonable way here. I'm looking for an altitude and an azimuth. We're going to focus on the rise point, which we decided will be east. All right, he got a phone call. I need to know an altitude and I need to know an azimuth. If someone says 66.5, I don't know which one they're giving me.
Is the altitude of the rise point 0?
Obviously, because it's on the horizon. Very good. So what you missed, Jeff, is Nina has identified that the rise point has an altitude of 0 because it's on the horizon. You haven't lifted up at all. Okay, that makes sense. What about the azimuth? Here's a hint. What's the azimuth?
90
Very good. Or east.
or east.
Okay, I like it. So 0 degrees altitude, 90 degrees or east, which is the same thing as saying due east if you're in the military or something, or if you're a boat captain, due east is east on the horizon. Now the reach point. The reach point is here. Altitude and azimuth. What have you got?
Is the altitude 42 degrees?
Why don't you look at the little diagram we made and think about that again?
Oh, 48?
That's right. The celestial equator to zenith is your latitude of 42 degrees. That means this angle up from the south is 48. What about the azimuth? That's the closest point on the horizon. What's the azimuth?
Mm,
180?
180 degrees or south. The closest point, if you're here, the closest point on the horizon to that dot is here, due south, okay? But it's, we'll just say 48 degrees and it's 180 degrees or south. How about the set point? Come on, Nicole, you can do this. What's the set point? Right there. Look, I just picked on you, Nicole, for fun. You got the altitude last time, right?
Yeah, I put 0 for altitude last time.
And what do you think about the altitude this time on the west?
Is it also 0?
Yep. And what would your azimuth be?
Mm,
Do you remember what the azimuth is? What's azimuth?
I'm sorry, I worked an overnight and I haven't slept yet, so I'm kind of like not alive.
I feel you. To be honest, Nicole, I only got a couple hours sleep last night, so I'm low energy Jeb Bush myself, okay? But well, I appreciate you being here, and I can imagine that sleep deprivation does not help astronomy. But let me put it this way, Nicole. I don't think it's good for me to just give you guys I mean, I want to give you guys the answers, and I'm going to do that. But I think it'll be better for you in the long run if you sort of struggle, sleep deprivation notwithstanding. Do you see what I'm trying to say? Here's what I want you to do. I want you to read the definition of azimuth while I drag this arrow mindlessly around the edge of the horizon.
It is the degrees along the horizon measured clockwise from north.
Okay, so that point happens to be on the horizon, which is helpful. How many degrees along the horizon clockwise from north are we? We start north, look at my red arrow, and we go
135.
No,
Oh,
you guys don't know your unit circle? What's 3 90-degree angles? 90 plus 90 plus
70.
sorry?
70.
270. Are you a nurse or something? What?
Me?
Yeah.
I work at a group home with disabled children.
Oh, wow. And you stay with them all night, huh?
Yeah.
Are they sort of in bed or do they go bonkers all night?
It depends on the kid.
Okay. All right. By the way, that point, the same thing as due west. All right. Well, the reason this concerns me is this is nice that you are willing to stay up to do this lecture, and I can imagine it's going to be pretty tough because it's a long ass day. Jeff is at work and he's bopping in and out, and that leaves me and Nina here. So part of me is wondering if we shouldn't be doing the pre-recorded lectures so that you can like catch a few Z's before doing this. I don't know. I'm trying to do this live thing because I thought it might be helpful, but today I was thinking, damn, I could have used some sleep too. So I don't know. We have to really think about this, you know? All right. Let's move on to part D. We're doing it now, so let's keep pushing. You guys got that? All right.
Wait, are we not doing? Oh wait, sorry, never mind. Disregard me.
This question has a lot of parts.
Does the sun ever appear at your zenith? If so, when? If not, why not?
So will the sun ever appear at the zenith in Rhode Island? You guys are going to need some help. What do you think, Jeff?
I think no.
And you think correctly. Let's take a look at the path of the sun again, because this could be helpful for us.
Can I ask for a clarification real quick?
Yeah, I'd love.
Did part C?
Yeah, what about part C?
I was just asking, what we did was just part C, and then the one before was part B, right? Okay.
Correct.
Okay,
Correct. The sun travels the path of the ecliptic. And each day the sun is pinned to the sky, like pin the tail on the donkey, if you ever played that game when you were a kid. And the sun will sit at one of these points, and then the earth will spin and the sun will rise and set. But each day the sun is drifting eastward along the ecliptic. It can go 23.5 degrees above the celestial equator, and it can go 23.5 degrees below the celestial equator. And that means the path of the sun in our sky can either be the red ring, it's on the celestial equator on the equinoxes, or it can be 23.5 degrees above the celestial equator, or 23.5 degrees below the celestial equator. Some of the drawings I had earlier show the path of the sun on particular different days. 21 shows it with the sort of north tilted to the right. This diagram is not as sophisticated, but it's better for us because they have north pointed towards the left, the way we like to do it. So it looks like for this observer, let me use blue because I'm used to doing that. The north celestial pole, Polaris, is like here, right? So Jeff, on the day of the spring equinox, the sun will start here and it will go do, 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 do. What will the maximum altitude of the sun be at noon on the spring equinox?
Degrees.
Look at your previous problem for assistance. What will the altitude of the sun be at noon on the spring equinox? That's too much? Have I got you?
Is it 48?
Oh, I think he's talking to someone. Yeah, that's right. Who said that? Nina? That's 48.
Sorry about that.
That's okay. I could see you got, so Nina correctly helped you there. She said the maximum altitude of the sun will be 48 degrees above
Thanks,
sea.
Nina. That's what I was going to say.
All right. Now, on the summer solstice, the sun will rise here and it will come up to a maximum altitude of what? So you know that from here to here, you know that to the celestial equator is 48 degrees. You know from the celestial equator to the sun on the summer solstice is how many degrees? So this is 48 degrees here, from here to here. How high above the celestial equator will the sun get on the summer solstice?
It's another 42 degrees from there to the zenith, right?
No, not 42 degrees.
No.
Where's that picture here? How high above the celestial equator will the sun be on the summer solstice?
23.5.
Okay. That makes this angle 23.5. So what will the maximum altitude of the sun be in Rhode Island's local sky at noon on the summer solstice?
72.5 degrees.
I think it's 71, right? 48,
70.
23,
Yeah, I'm sorry.
71.5. Good. Anyways, Jeff already knew the right answer. I'm just sort of explaining that. No. The sun will not reach the zenith in the Rhode Island local sky, but only reach a maximum altitude of 48 degrees plus 23.5 degrees equals 71.5 degrees south at noon on the summer solstice. In other words, we're explaining why the sun can't reach our zenith. We're explaining that it could only get to a maximum height of 71.5 degrees based on our latitude and on the tilt of Earth. Kyle, you're jumping in kind of mid-homework here, so you're probably going to have to rewatch this later, but you can start copying stuff down if you want to.
Okay, that's all right. I can rewatch it.
Maybe since we're only on 41, we're going wicked slow today because nobody knows what's going on. Maybe you can start copying at 47 and that'll save you some time, okay?
Oh, that's a good idea.
So be a passive observer until we start the next question. We really have to move faster. Can someone read me question E? Because we lost our friend Nicole.
He says, what range of declinations make a star circumpolar in your sky?
All right, I'm going to erase this. What range of declinations make a star circumpolar? Okay, a range of declinations means there's two numbers. We're going to go from a low number to a high number. That's what range means. So let's take a look at circumpolar stars. Here. I might have given you a little spiel about them last time, but it was short-lived. If you point a camera towards Polaris and you take a long exposure photograph while the Earth spins, you can see stars kind of spinning around Polaris. Some stars are so close to Polaris that they become circumpolar. And circumpolar means never rise or set. They're so close to Polaris in the sky that they kind of orbit, but they don't go below the horizon. In other words, this star here is circumpolar. It does not set. This star here is not circumpolar because you can see here it does set below the horizon. We're looking for a range of declinations. Declinations are measured positive and negative from the celestial equator, okay? All of the stars that you see here are circumpolar. And when you translate this to your local sky, well, here. These show you the tracks that stars make as Earth spins. Each of these rings corresponds to a declination. And remember, the declination measures degrees plus or minus from the celestial equator. I'm going to close one of my windows because it's really noisy here. Hold on, guys. All right. Sorry, it's such a beautiful day out, but the sounds of the city were just getting to me. So the celestial equator has a declination of 0 degrees, and then we measure up to positive 90, and we measure down to negative 90 when we do declinations. We need to find the range of star tracks that are circumpolar, right? So let's see if you guys can help me by identifying some declinations here. Can someone give, all right, first of all, let's start easy. What's the declination of the red ring?
0.
Okay. Give me a reasonable guess. What would be the declination of the blue ring? It looks like it's about 1/3 the way up the globe. So I think you guys need to review the definition of declination. I tried telling it to you a second ago, but that wasn't good enough. That didn't help you because you're all zonked. So I need someone to regurgitate the definition of declination for me.
Degrees plus or minus from the celestial equator.
All right. So I'm asking you to take a reasonable guess. How many degrees above the celestial equator is the blue ring? That's what I want you to do.
It's not 23.5, is it?
No, I think that's
40-ish.
just supposed to be a third of the way up. So
40, 45, somewhere around there.
I wouldn't say 45. Here's why. Whoa, that arrow is too big. Hold on.
Yeah, he did send me.
Here's why. Where do you choose the size of your shtick? Oh, right there. Okay. 45 degrees is half of 90. So 45 degrees would be like the green arrow. This blue arrow is somewhere between 0 and 45. I suggested that it's 1/3 the way up the globe. So try again. What's the declination of the blue ring? Not positive 45, but how many degrees is it from here to here? Y'all scare me a little bit. Okay, let's try an easier question. How many degrees, let's try something simpler. How many degrees is it from the red ring up to the North Celestial Pole? Oh, snap. Is there not one person who can tell me how many degrees it is from red ring up to the North Celestial Pole? You can see the arrows that I'm drawing, right?
Yes. Is it 90?
Hell fucking yeah, it is. It's perpendicular lines when two lines meet and make a capital T. You guys just gave me the willies there. I would hope that you would recognize a 90-degree angle when you see one. If I do this, that's kind of a 90-degree angle. Even if it's tilted on its side, two perpendicular lines are always going to be 90 degrees, right?
Is the declination from the red line to the blue line 22?
I mean, that's a reasonable guess, but I was thinking it was 1/3 of the way up the globe. So what I wanted you to do is take 90 and divide it by 3. Positive 22 would be a reasonable guess to the blue ring. It's not really labeled, but I was thinking it was 1/3 of the way up. So I was thinking it was positive 30. Let's keep going. Give me a reasonable declination for the purple ring.
From the red ring to the purple ring?
Yeah, that's how declination works, from the celestial equator up. So what would be the declination of the purple ring?
120 degrees.
Nope. 120 degrees would be more than 90 degrees. There is no such thing as a declination of 120 degrees. Sorry, Kyle, because declinations go from -90 to 0 to positive 90.
Is it
So this is 0 degrees. This is plus 30. What about the purple ring?
45?
45 is halfway up. I think
60.
yeah. Honestly, 45 wasn't a bad guess, but I'd say positive 60.
Okay.
And you know that the declination up here is positive 90.
Yeah.
Okay, Polaris is definitely a circumpolar star. So the greatest declination that stars can have and be circumpolar is positive 90. The lowest declination is when the star just grazes your northern horizon. So we actually need to get the declination of the northern horizon. To do that, recognize that the angle from here to here, that's the declination, it's the degrees above the celestial equator, is 90 degrees minus this angle here. And this angle is the altitude of Polaris. Do you guys remember what this angle is?
42.
All right. So what should the declination of your northern horizon be? From there to there?
48.
48. And positive 48 to positive 90 are the range of stars that are circumpolar.
Can you like briefly explain circumpolar again?
Circumpolar stars never rise or set.
Okay.
So if you go out at night, people make a cottage industry of taking cool pictures of circumpolar stars. If you, during the course of the night, Earth spins slowly, so you don't notice the stars rotating. But if you take a long exposure photograph, you can watch the stars kind of orbit around Polaris.
Oh, okay.
Circumpolar stars are ones that are so close to Polaris in the sky that they cannot dip below your horizon. So all of these stars here are circumpolar, except, let's use the circle tool for this. The very last circumpolar star is the one that just barely grazes your northern horizon. Once their declinations get lower down, they set below your horizon. So that circle is not circumpolar, okay?
So they never rise or set, so you can't see them?
You can always see them. They're
Oh,
always up.
okay, I get it.
Polaris is circumpolar and it's always in your sky.
Yeah.
The
Okay.
Big Dipper is almost circumpolar, which is why you can see the Big Dipper at some point during the night throughout the entire year.
Okay.
One of the reasons why the Big Dipper is popular. There's also a range of stars in part F that are called, well, I call them anti-circumpolar stars. There are some stars that you can never see from Rhode Island's latitude, and that's because they're too far below the celestial equator on the celestial sphere. Those stars have a declination of -90 at the south celestial pole, all the way up to a ring which just touches your southern horizon. Your southern horizon has a declination of -48 degrees because it's 48 degrees below the celestial equator. This stuff can be kind of tricky, but we're sort of running out of time here. So for part F, they ask, what is the range of anti-circumpolar stars? The answer is they go from -90 degrees to -48 degrees. Okay. This office hours has been pretty rough. One reason is that we didn't quite get as far as I would have liked to in the lecture. Another reason is, well, you guys still haven't learned your definitions of things yet. And I don't know, maybe lack of sleep is also contributing to it. We've got at least 3 more problems to do. Maybe we can try to squeeze one more off. What's 47? Sorry, Nicole, can you see all that? Are you writing that down? Okay. I got to think about what I'm going to do here. I believe in one of the other office hours, I covered more of these questions. Let's see if, what is 48? Okay. How do I want to do this? I'll tell you what we're going to do. This is gonna get a little ugly, but I think here's what my plan is. We're going to take a little break, okay, before we start lecture. I am going to work the answers to the rest of the homework questions into our lecture today, okay? We're also supposed to meet on Friday, right? I think what I'm going to do is I'm going to pause homework operations, and I'm not going to have us do a homework on Friday. And I've got a couple of different reasons for that. We're in this death cycle where the homework questions are like a little before where we are in lecture, and I want to kick that problem so that the homework is after the lecture parts. Also, it's Friday, and none of us feel like coming to school on Friday. So shortening the day will make it suck less. Does that sound like a good plan? I think that's a pretty good plan.
No office hours on Friday.
No office hours on Friday, but we will probably do a lab, a very short, easy, basic lab. Okay. And lecture, of course. We have to do lecture. Now, we still have 3 homework problems left to do today. I'm going to just incorporate them into lecture as sample problems. Let's take a 10-minute pause or so. Oh, wow, it's already 11:57. My phone clock and my computer clock are not synchronized, and it's driving me absolutely nuts because I keep using the computer clock. Okay, anyways, that's a me problem. Let's take 15 minutes, and 15 minutes we'll do lecture. Sound like a plan, guys? I'm going to start my phone timer now for 15 minutes, and we'll give ourselves a little break, and we'll come back after that. Okay, good luck. Okay, friends, we're back for our 3rd lecture. Lecture 3 is going to contain the answers to some of the homework problems that we're going to do today. Our homework was a little bit ahead of where we were in lecture, which was brutally painful, as we all discovered during the office hours. Today, I will work in the answers to the other 3 questions as example problems after I introduce the topics. I also want to remind everyone watching later that I've made the decision to not have an office hours or homework due on Friday. That will give us time to get our lecture ahead of where the homeworks are. It's part of the weirdness is usually during the spring and fall semester, I do homework after lecture. But what I discovered in past years is that if you guys start lecture at noon and then we do lab at 3, by 5 o'clock, people have all kinds of crap going on like dinner and they have to travel and stuff. So it didn't make sense to do office hours after class. It made sense to do it before class, but it creates a little bit of awkwardness. So let's start by just showing you on the board. I did something like this yesterday and some people got confused. So I want to spell out on the board real quick what is going to be due this week. Okay, I'm going to leave those up. So this week, we had a Wednesday and a Friday class. Wednesday, we do homework 2, lab 3. Friday, there will be no homework 3, but we will do lab 4. So that Sunday at 11 p.m., you guys will owe me homework 2, lab 3, and lab 4. Make sense? I thought sort of spelling that out might help alleviate some confusion. Okay, cool. What we're going to do for starters today, you'll remember that in our last class, we learned 2 coordinate systems. We learned the horizon system, which has altitude and azimuth to describe the position of stars in the sky. We played around with that in our office hours. We also learned the equatorial system, which is more complicated. That's right ascension and declination, and those are like latitude and longitude for the sky. Afterwards, we practiced the equatorial system. You should have in your notes, Nina or Nicole, if you can look back, you should have the right ascension and declination of the 4 key points in Earth's orbit. Did we do that?
Yes, I'm just looking for it.
I just want to be 100% sure I'm not confusing you with the other class.
So like the spring equinox and the solstices, you mean?
Yeah. We
Yeah.
listed their right ascension. So that means we practiced the equatorial system. Now that was a week ago and you've probably forgotten it all, but I did it. Okay. Today we're going to practice using the horizon system a bit. And you're going to recognize this little module I'm going to do. It would have been quite helpful for today's homework. We're going to learn how to make a 2D view of the Rhode Island local sky, all right? And you'll remember we kind of did something like this last week when I taught you how to draw the three-dimensional view of the Rhode Island local sky. Turns out sometimes making a quick 2D picture is helpful. Hopefully you guys purchased some plastic rulers. That will really go a long way here. If not, wing it, I guess. Leave yourself a good amount of headroom here, okay? And halfway down the page, make a line that's about, I don't know, 10 centimeters long on your page. And mark the midpoint of the line at the 5 centimeter mark. We're going to attempt to draw a dome. And one of the tricks that I use to draw a dome is you guys would use a 5 centimeter radius, and at 5 centimeters, mark a whole bunch of different dots so that you can sort of see where the arc should be going. This is just going to help us connect the dots a little bit when we draw in our dome. Okay. And now I can connect these dots to make, I'll put one more in since I'm going buck wild here. That ought to help me make a nice good dome. So it's going to connect the dots. Kind of a good guide for your hand. And sure enough, you can see a reasonably good dome comes out of there. Let's put an observer dude at the center of the field. It's always important that we choose directions. This local sky is going to be a slice from north to south. That makes this dome our meridian. And so we're making a north to south slice of the 3D local sky. It's important to specify which direction is north. I'm even going to shade in a few lines. This is not really a 3D drawing, but this will help trick you into thinking about the 3D aspect of it. Okay. Let's draw a line right through the top of our observer's head. That line obviously points to the observer's zenith. So I'm going to mark it with a little Z. I'm also going to draw in the north celestial pole and the celestial equator, or part of it anyways. So the north celestial pole should be about almost halfway up the sky, towards the north. Label that arrow NCP. Let's also put the star Polaris here so that we remember Polaris is roughly at the north celestial pole. I'm also going to draw, I can't draw the full celestial equator, it runs east to west, but the celestial equator is perpendicular to the north celestial pole, and I can draw the point where it intersects my meridian. So I'll make a dashed line up there, and I'll label this CE for celestial equator. The two-dimensional view of the local sky is nice because we can focus on the geometrical relationships between all of these angles. And what we'll do is we'll play a little game here, a little mini game. We're going to label these 4 angles with the first 4 letters of the Greek alphabet. They are alpha, kind of looks like a Jesus fish. Beta, kind of looks like a squiggly bee. Actually, let me make my beta even better. Here's beta, right? Gamma looks like a squiggly Y. And delta looks like a squiggly D, or a musical note. Alpha, beta, gamma, delta. It's customary to use Greek letters to represent angles in astronomy. And that's because the Greeks loved geometry. So it's a little nod to them. Also, once you get used to that practice, as soon as you see a Greek letter, the astronomer starts to think, I bet this is an angle. I bet that's what that is. Okay, let's try a little game. One of these angles, alpha, beta, gamma, delta, is a direct representation of your latitude on Earth. Which one of those angles represents your latitude? Today's homework might have been helpful for that. I'm still deeply unhappy with my gamma there. Which of these angles represents your latitude? Anyone have any thoughts about that?
Gamma.
No, gamma is not a good representation of your latitude. What's the definition of latitude?
The degrees north or south of the equator.
Okay. Another way to think about it is it's the angle between the equator and your feet. It's the number of degrees north of the equator. It's the angle between your equator and your feet. So the equator points towards the celestial equator, right?
Yes.
So
Beta.
huh?
Beta.
Beta represents your latitude. Very good. The angle between the equator and your feet is the same as the angle between the celestial equator and your zenith. Earth's equator points towards the celestial equator. Your feet and your head point towards the zenith. So if Earth was tilted, say like this, the equator would be pointing towards the celestial equator, and beta would be how many degrees your head is pointing north of the equator, right? Okay, so we've convinced ourselves. Did I lose my damn black marker? Is this it? Beta is our latitude. Let's try again. One of these angles, alpha, beta, gamma, delta, is a direct representation of the altitude of Polaris. Which one of these angles represents the altitude of Polaris?
Delta?
Delta is correct. How'd you know that?
Because it's the angle in between the North Celestial Pole and North.
That's right. The altitude is defined as your degrees above the nearest horizon. This point here is obviously your nearest horizon. It's your northern horizon. So delta represents the altitude of Polaris. Now, we kind of worked out these numbers for Rhode Island's local sky in our office hours, but let's do it again. What is the latitude of Rhode Island?
42 north.
So this angle is 42 degrees. What about gamma? What should gamma be, considering that this is a 90-degree angle?
48.
Then gamma should be 48. What about delta?
42.
What about alpha?
48.
Very good. So alpha and gamma are the same, beta and delta are the same. There's probably a name for that in geometry when you have two right angles. I don't, complementary angles, I forget what the hell it's called. I took geometry a long time ago. Now, we worked out those numbers for Rhode Island's local sky. But in general, this angle is always going to be an observer's latitude. The angle between the equator and your feet is always going to be the angle between the celestial equator and the zenith. So beta is always going to be your latitude. And it's also true that there's always a 90-degree angle between the equator and the North Pole. And there's always a 90-degree angle between the zenith and the horizon. So anywhere else you go on Earth, these relationships will hold, where this will be your latitude, this will be your latitude, and these two angles will be 90 degrees minus your latitude. That means we've discovered a fundamentally useful result that is helpful anywhere you go on Earth, and it sounds a little something like this. The altitude of Polaris is equal to your latitude. I want you guys to put a box around that. That is a key result that is easy to remember, and it will help you solve many types of problems in astronomy. In fact, this might even be considered to be the basis of celestial navigation. If you know how the stars change as you travel around Earth, you can use stars to locate your latitude, and you can even use timekeeping devices to locate your longitude. Let's try a quick problem with this. Do you guys have this? Nicole, let me know when you're good. You're good? Okay. I'm going to erase this. Kyle, I think you should be writing this stuff down, but that's just me. Hell, you can do anything you want to do. But
I take screenshots of it.
okay. Believe it or not, Kyle, and this is me butting into your business, which I have no right to do. Well, the nice thing about taking screenshots is you can sit there and listen and focus on what's being said. But I believe there is a value to writing this stuff down with your hand. I think it helps you memorize. Now, that's your personal learning journey, so I'll let you do it your way. But I want to at least put that thought in your head. I don't know everything, but that's my suspicion.
I screenshot during class, but then I write it down after so that I don't lose focus on what you're saying.
That is a really good idea. Okay, if you take the time to do that, then that is impressive. I like it. I like it a lot. All right, so I'm going to erase. Okay, before I work on our next problem, our next problem is on celestial navigation. I want to try a little sample problem based on what we just did, and then I want to talk to you guys about timekeeping. That lecture will sort of fill in the gaps for our celestial navigation lecture.
I have a question about Polaris.
Yeah, go for it.
So when I was a kid, I read Marvel comics, and like they have like these superpowers, but like some of it's like some characters it's based off of science.
Yep.
There actually is a character named Polaris.
Okay, what's his special power?
Her power is
her power, sorry.
She gets like magnetic energy like from the constellation Polaris, and like
What?
she can like make the aurora boreals happen, like the lights in Alaska, if she wants to. So is there actually a connection between Polaris and like those like green lights that you see in Alaska, or am I just thinking that because I read the comics?
I think you're thinking that because you read the comments and they bamboozled you a bit, but let's start by talking about what I know about Polaris. So Polaris is a star, North Star, and it's in a constellation called Ursa Minor, the Little Bear. And the Little Bear actually has some other parts to him. Like, for instance, this is supposed to be the tail of the bear. That's the butt of the bear. And then the bear like comes out here and he's got like a snout and then maybe even like some claws or something like that. Okay, so Ursa Minor, it's also colloquially known as the Little Dipper because these are the brightest stars in the constellation. Now, I say that these are the brightest stars, but from Warwick's or Providence's sky, I can't see any of these stars in the Little Dipper. Usually you can see the stars in the Big Dipper, the Big Bear, Ursa Major. You can use the Big Dipper to find Polaris. These two stars are called the pointer stars, and they kind of make a line towards Polaris. That's usually how I find Polaris, because it's too faint to see these stars. Polaris turns out to have a binary component. It's also something called a variable star. But what I think happened with that Marvel comic is Polaris probably does have some magnetic field activity. As you will see when we discuss the sun in our class, the sun itself has a lot of interesting magnetic activity. And by the way, some of the sun's magnetic field activity creates the aurora borealis on Earth. But Polaris's magnetic field, as far as I know, is not known to be of extraordinary strength. I suspect they're confusing Polaris with something called a pulsar, because they both begin with P and have roughly the same number of letters in them. A pulsar is a very magnetic star that spins and rotates quite fast and beams a magnetic jet towards Earth. It is not, even pulsars are not, right, shit. Pulsars are not capable of creating aurora borealis, only the sun is. So here's a little animation of a pulsar. It's got such a powerful magnetic field that it points towards Earth. Now, the truth is somewhat complicated. Polaris probably does have a magnetic field, and I guess that because our own sun has a magnetic field, and stars often have magnetic fields associated with them. But there's no effing way Polaris's magnetic field would be powerful enough to trigger aurora on Earth. The sun, however, does. So what that sounds like, Kyle, is it sounds like they took snippets from science and they glued them all together in some creative way. That's okay. The cool thing about fiction and art is you can kind of do whatever the F you want and no one can tell you otherwise, right? That's what's fun. But if you're interested in the truth or, you know, what we really know, Polaris will not trigger aurora on Earth. But there's little bits of truth to all of it. You know what I mean? And honestly, I don't think I would have gotten into science if I had not been inspired by science fiction, some of which, looking back on it, was pretty hokey. So if comic books and Star Wars are the gateway drug into studying physics and astrophysics, then those are good drugs. But ultimately, there are drugs in which sense that they are bad for you. So there are my thoughts there. Okay. Anyways, those are things I know about Polaris. And if you want to learn more about that kind of stuff, Kyle, you're going to have to pay another $550 and sign up for my Astronomy 1020 class, where we talk about some exotic objects like that outside of our solar system. In this class, however, we are going to study the aurora borealis, not only on Earth, but on other planets, and you will learn about the magnetic fields of the sun. So you'll get to learn some stuff like that before the class is over. Let's first try a little sample problem based on that exercise that we just did. Now I remember where I wanted to go. See if you can answer this question, which was actually the same thing as one of our homework questions, 41A. So question 1. Describe the position or location of Polaris in the Rhode Island local sky. So I'm hoping this question is somewhat easy. I'm hoping you know what to do, but let's see where you are. This will be a test of your memory or skills. How would I describe the position of Polaris in the Rhode Island local sky? What's the best way to do that? Now, I just told Kyle you can use we should use altitude azimuth. That's right. So first order of business, Jeff has correctly pointed out that we want to use the horizon system because it's our local sky. And that means we need an altitude and an azimuth. Can you give me those two, Jeff, or?
It was 42 degrees and 0 due north.
Good. So the altitude is clearly 42 degrees. We just learned that the altitude of Polaris is equal to our latitude. The azimuth Since azimuth is the same as direction, we'll just say north. All right. Excellent. Okay. How about question 2? Describe the position of Polaris at the North Pole sky. Once again, we're going to want to use the horizon system because it's a local sky scenario. So I want an altitude and I want an azimuth. Who can do this? Anyone? Go for it.
It's going to be 90 and 0, right?
Okay, let's start with the altitude. That was good. How did you know the altitude of Polaris would be 90 degrees?
Because Polaris is at the celestial pole. It's at 90. It's directly above you if you're at the North Pole.
That's one way to look at it. Another way to look at it is to use the rule that we just discovered in our class. The altitude of Polaris is equal to your latitude. If the latitude of the observer is 90, the altitude of Polaris will be 90. Now, I want to take issue with your azimuth a bit. And to help you understand why, Jeff, let me show you a kind of crappy cartoon from the book, trying to imagine what it would look like from the North Pole. And you kind of mentioned something about this earlier, so this is kind of cute. Look at these two pictures, left and right, showing you 99, a global sky view of the North Pole and a local sky view. Obviously, the global sky is on the left, the local sky is on the right. This is what it looks like when you're the observer. This is what it looks like if you're in outer space. Sure enough, we can see that, although they didn't label it here because whatever weed-smoking artist they hired to do this job was not on the ball that day, but Polaris should be right here, okay? And sure enough, we can see that the altitude of Polaris, the degrees above the horizon, is a 90-degree angle, just like Jeff said. Jeff, what's the definition of azimuth?
Azimuth is from north to south angles. I'm trying to think of the wording for the proper. It's the degrees from north to south on the horizon.
In which direction, clockwise or counterclockwise?
In a clockwise direction.
Right. It's degrees from north clockwise. Here's something to think about, Jeff. When you get to the North Pole, north, south, east, and west break down because from the North Pole, every direction along the horizon is all south. So that's one reason it's kind of hard to define the azimuth. Another reason we saw in our office hours, if you're at the zenith, where Polaris is from the North Pole, every point along the horizon is equidistant from the zenith. So there is no one point on the horizon that's closer in any sense. The zenith does not have a well-defined azimuth. So since Polaris is at your zenith, the azimuth is actually undefined. The word they use in mathematics is degenerate. The azimuth of the zenith is degenerate. It's multi-valued. But 90 degrees means it's at the zenith. Fine. Nice exercise. Someone besides Jeff, Kyle, Nicole, Nina, you try question 3.
I can try question 3.
I like that. Describe the position of Polaris in Ecuador. And I'm pretty sure Ecuador is on the equator, right? Yeah, that's why they do that. Ecuador. The capital is Quito. And Quito looks like it's on the equator. Is that how you pronounce that? Okay. Where would Polaris be in Quito's local sky? Kyle?
Altitude -60 degrees.
That's not possible. There's no such thing as an altitude of -60. Polaris will be in the local sky, and altitude is defined as degrees above the horizon. A negative altitude would mean you were below the horizon.
Oh, 45 degrees altitude.
That's not correct either. You need to use the rule that you should have screenshotted below your two-dimensional local sky. What's the rule, Kyle?
I'm trying to pull it up.
Do you know what I'm referring to?
Yeah.
What's the rule? I like your gumption, son, anyways.
Altitude is degrees above the horizon.
No. But by the rule, I mean, there is a rule for finding Polaris in your local sky, and you learned it 5 minutes ago. What's the damn rule?
It's the altitude of Polaris is equal to your latitude.
Hey, Nicole, what's that? Let's pause here. What's that kitty all about? Show us that kitty. What the hell? Oh, it's a doggy. Look
This
at
is
that guy.
Shiloh.
Hey, Shiloh. What a cute pooch. We want to see a whole lot more of that guy or that girl. Is it a guy or a girl?
It's a boy. He's an old man. He's 11.
Oh, wow. Yeah, he seems to have mellow. It looks like you've got like a Shiloh and themed inspired pillow behind you there,
Yeah.
too. Love it. I love it when people show me their animals. That's really fun. That was cool. Okay, so Nina, what were you saying again about the altitude of Polaris?
The altitude of Polaris is equal to the latitude. Or to
And
your
what's the latitude in Ecuador?
0.
Right. So what I wanted you to do, Kyle, is to say Ecuador is on the equator, right? Here's Ecuador. And if the latitude is 0, then the altitude of Polaris has to be 0 degrees. And what's the azimuth, Nina?
The azimuth would then be,
This is kind of like what color is an orange, or who is buried in Grant's tomb, you know? What's the direction of the North Star?
north.
Right. Okay. Polaris is always going to be located in the direction north. That's how you freaking figure out where north is when you're in your sailboat at night, right? Polaris tells you north. Convenience that there's a star so close to the North Celestial Pole. Celestial navigation in the southern hemisphere is more tricky because there is no star located at the South Celestial Pole. That's annoying. Okay, this is how we use the horizon system. Expect me to ask questions like this on a test, okay? I wanted to practice. I'm erasing. You good, Kyle? Let's talk about time and the path of the sun, okay? I want to talk to you guys about, okay, timekeeping, the science of keeping time, is deeply related to astronomy. The branch of astronomy that is associated with timekeeping is known as astrometry. Astrometry concerns itself with the positions of stars, coordinates of stars, and using them to influence how we keep time. Let's think about this fact. The sky is a big clock, okay? Literally, ancient Mesopotamians, people who stopped traveling after, you know, herds of elk or whatever and started growing crops, had to use the sky as their timekeeping device, and they got very good at observing the sky and predicting its motions. Astronomy is even older than science or mathematics itself. You've got some options, but usually, if you're agricultural, we mostly keep time by the motion of the sun, okay? And the sun has two motions. There is the daily motion. The fancy term for the daily motion is diurnal. The diurnal motion of the stars, the diurnal motion of the sun is their revolution around the sky. And as Nina now knows, she seemed a bit confused during office hours in this point, the sun travels in our sky east to west, right? However, there's a secondary motion. There is the yearly motion of the sun, and the yearly motion of the sun is eastward by 1 degree per day, which corresponds roughly to 4 minutes per day. I will remind you that a 360-degree spin divided by 24 hours, do you guys remember what that's equal to? Punch it into your calculators. Maybe that'll help you remember it.
15 degrees per hour.
That's right. The sky rotates 15 degrees per hour. That's mostly connected to the diurnal motion of the sun. By the way, 1 degree per day along the ecliptic. I should have thrown that in there for completeness. 1 degree per day along the ecliptic. Sorry about that. Okay, let's look at the pictures again. So how do I want to do this? There's a lot I want to say. I'm just figuring out the best way to put it. When you look at the ecliptic and compare it to the celestial equator, you can see that the sun can sort of travel back and forth from 1 to 4 different positions. On the spring equinox, the sun is located here at the celestial equator. And then each day, the sun will slide along the ecliptic eastward until it reaches a maximum height, 23.5 degrees above the celestial equator on the summer solstice. And then it will continue sliding eastward until it's there, back on the celestial equator. And it will continue sliding into winter, where it will be 23.5 degrees below the celestial equator and back. What does that look like from your place on Earth? It looks like this slide here. The sun will either travel on the equinoxes along the celestial equator. So during the day on the spring equinox, it rises in the east and it comes up and it crosses your meridian at noon and it sets in the west. Each day it gets a little bit higher in your sky. On the day of the summer solstice, it will rise north of east, cross your meridian and set north of west. On the winter solstice, then it will wind its way back down, circling and circling and circling and circling. And then it will wind its way back down here. One can keep time by the sun. And when you keep time by the sun, you use a sundial. The sundial will just track the motion of the sun, and the shadow of this stick, remember that this stick here is called nomen. Oops, I like this word. I just think it's a funny word, nomen. So in a sundial, you've got a nomen and you've got a, you've got a nomen here. And this is maybe the dias. I don't know what that's called. And then as the sun travels around the sky, the shadow on the stick, as the sun moves to the sky, will move its way around the hours of the clock. Each hour, the shadow will move by 1 hour along this clock. That's probably how time was invented. And when you track the motion of the sun, that's called mean solar time. I'm sorry, apparent solar time. More notes. Okay. So first, let's talk about something called apparent solar time. Apparent solar time is time by a sundial. Okay? It's cute. It's natural. It's fun to say nomen. And all you really need to build a clock is to build yourself a sundial that points towards Polaris, and the shadows will basically do the rest, right? However, there's a problem with apparent solar time. The sun does not move throughout the sky at a consistent rate throughout the year. Here's where it gets messy. The sun's rate, how do I put this? The sun's drift across the sky varies throughout the year. One way you can demonstrate this is through photography. Let me show you a kind of cool picture that this guy took, or this woman took. I don't know who took it. Some clever photographer or astronomer went out probably every, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So they probably went out every 2 weeks, maybe twice a month. And they took a picture of the sun at noon, at exactly noon, every 2 weeks. And they did something kind of clever. They left the shutter open for the entire morning on 3 of those days. So this line that you're seeing here, remember, you're squishing a 3-dimensional surface onto the sky, but I'm guessing that the observer's meridian is an arc that goes sort of like that. Remember, the sky is a dome, and when you flatten it onto photography paper, things get a bit weird. What I'm noticing, and what I want you to notice, is that the sun does not appear at the meridian at noon every day of the year. The sun can drift ahead of the meridian or behind the meridian by up to about 20 minutes, I think, throughout the course of the year. This is a very famous shape in astronomy. This shape goes by the name of an analemma. Let's write that down. An analemma. The analemma is this cool figure 8 that the sun makes when you try to photograph it throughout multiple days on the year. I'm going to explain it in a second, but first let me ask the class a question. Do you know what day this was here? What day was that? I expect you to know the date. You see what's happening. They left the shutter open and they actually watched the sun drifting across the sky for its diurnal motion. What is the date at which the photographer left the shutter open?
Is that the spring equinox?
No.
Summer solstice.
That's the summer solstice. Nina, the summer solstice is when the sun is highest in the sky. How about this date? So this was June 21st, right? That's the summer solstice. What about the second arc right here? What was that date? No? Nina, why don't you try?
Is that the spring equinox?
That's right. So that's March 21st, right? How about down here? What's that date?
Winter solstice.
That's the winter solstice. That's December 21st, right? Okay. Why does the sun not make, I can't even do it. Why does the sun not make a consistent rate throughout the sky? It has to do with two kind of complicated things, and no one's going to really follow this, but I'm going to try anyways. On the day of the summer solstice, so here's the thing. The sun is going from east to west, right? But the sun has a very slowly eastward drift caused by Earth's motion around the sun. And that means every day the spin of Earth is working contrary to the orbit of Earth, where the spin of Earth is making the sun travel west, but the orbit of Earth is making it drift backwards or east. During the summer solstice, when the Earth is spinning like this, the direction of the sun across the sky is completely east to west, and that slows the motion of the sun. During the equinoxes, however, that slows the motion of the sun. During the equinoxes, the sun's drift across the sky has a north to south component as Earth spins, and that actually speeds up the motion of the sun around the sky. The other reason for the analemma is that Earth's orbit is not a perfect circle, and Earth travels faster on its orbit at perihelion closer to January. So what you can see happening is part of the reason the sun's kind of drifting ahead or behind noon, the rate changes throughout the year, partly is because of its north to south component of motion, and partly it's because when the Earth is moving faster around the sun, you slow or speed up the motion of the sun more than average. Whatever. Just take my word for it. The sun's drift across the sky changes. Now, why is that a problem? If you live in a mechanized society where you have to decide how many hours a lecture is going to be, or maybe how many hours your shift at the factory is going to be, it's not helpful to keep time by a sundial, because sometimes of the year you'll be making more per hour, and sometimes of the year you'll be making less per hour because the length of an hour keeps changing, and that's fucked up, and we don't like that. We like time to be regular and have a smooth, consistent flow. So eventually we got to the point where we'd hire some Swiss watchmaker who would use the analemma to create an equation of time. And rather than actually track the real sun across the sky, they track the average rate of motion of the sun across the sky. They basically work out what's the fastest drift and the slowest drift. They divide it by 2, and then you're basically keeping time by a fake imaginary sun, which actually has a smooth, consistent rate across the sky. That is what your watches do. And you keep not apparent solar time, but you keep time by a watch, mean solar time. And there's a complex calculation that goes into figuring out how fast the hands on your watch should run. This is what astronomers are sometimes hired to do. So you keep not apparent solar time, but you keep mean solar time. This is time by a mechanical clock, okay? You keep this. This is what you keep track of in your daily life. And it's basically the average rate of the sun on the sky. And the details of that are over your pay grade, so I won't get into it too much. Whether you are keeping apparent solar time or mean solar time, both times have this in common. The day, keeping track of it, starts at midnight, right? 00 hours. I want to expand upon what that means for just a second. Let me know when you guys are done with this because I need to erase. I need my board back. Nicole, you still writing? Give me a thumbs up or something when you're done. All right, I'm erasing now. Let's imagine how the sun rotates through the sky. So I'll make a quick and hasty three-dimensional drawing here. So because I've done this a lot, I can kind of make a quick and dirty drawing of the local sky. This is your zenith. And you guys know what this thing is called, right? What's the name for this arc? Impress me with your astronomy vocabulary.
Meridian.
Right. Now I'm going to expand on that definition. This meridian passes through the zenith and is sometimes referred to as the zenith meridian. It's the meridian that passes through your zenith. You guys also know that there's a part of the sky that we cannot see because it's below our horizon. And that part of the sky goes like this. We normally don't think about it because that part of the sky is not visible to us. Okay, I didn't do a great job in that dome. Let me fix that. Okay. There's another vocabulary word for the part of the sky that's directly below your feet. That is called the nadir. This purple line that I drew is sometimes referred to as the nadir meridian. During the course of a day, let's choose the spring equinox, for example. The sun will wind its way across the sky. It'll start here. It'll travel up through the south, back down, and then the sun will go below the sky at night. The day starts, we start our 24-hour clock when the sun crosses the nadir meridian. So the day starts 00 hours. That's where the day starts. We like to design our day so that this is 12 p.m. or 1200 hours. That would mean, what time will it be when the sun rises in the east in general? So here's the east. Here's the west, right? Pardon?
a.m.
One more time, Nina.
6 a.m.
Yeah. We like to design time so that when the sun is here, when it's there, that should be 600 hours, 6 a.m., right? And we like to design it so that when the sun is over here in the west, that's 1800 hours or 6 p.m. So if we're doing it right, the sun rises at 6 a.m., crosses your meridian, sets at 6 p.m., and the day starts again when it crosses your nadir meridian. This is how you do it with apparent solar time. And in a way, mean solar time kind of keeps a similar calculation, but it tries to subtract out the forward and backward motion of the sun. Obviously, the time of day depends upon your longitude. If you're spinning on a globe, it might be nighttime for you in America, but daytime for someone in Australia, right? It's always daytime somewhere on Earth, and it's always nighttime on Earth. For this reason, over time, when people began traveling across the globe at faster and faster rates, it became necessary to divide the Earth up into time zones. And let's talk briefly about time zones. So the original motivation was actually during the building of the Transcontinental Railroad. And you may have, seen some Westerns about this and stuff, people working on these immigrant communities working as basically very low paid servants building these railroads across the country. People began to have the ability to travel in a single day or in a couple of days from New York City out to Ohio and then on to California and other places in a matter of a couple of days. Because these are wide ranges in longitude, people had different clocks, one for New York time, one for Chicago time, one for Denver, Colorado time, one for San Francisco and Los Angeles time, and none of those clocks were the same. So it was actually the railroad companies and the railroad barons that decided to break the United States up into wedges of 15 degrees and have everyone keep the same clock for one of the cities in the middle of the wedge. So rather than the good and oldie days when you'd have a clock for Providence and a clock for Boston and a clock for Philadelphia, one of these railroad companies said, you know what? From now on, everyone in this chunk is all going to keep the mean solar time of Philadelphia because that's in the middle. And that's another reason why the sun is usually not exactly at your meridian at noon, is because you're actually keeping the mean solar time of Philadelphia, not Rhode Island. This turned out to be very helpful because people could simplify their train schedules and know what time it was going to be in each of the cities when they arrived. This was such a good idea that eventually the entire world followed suit and developed something called universal time. That's where you break the Earth into a set of time zones, each 1 hour or 15 degrees in wedge, and everyone sets their clock to the prime meridian, which is called Greenwich Mean Time. Let's take some notes on this because this is important. So the note we want is US rail travel led to the creation of what we would call standard time. Standard time is where the entire East Coast keeps, I believe it's Philadelphia, mean solar time. So we're not keeping apparent solar time because that varies. The East Coast keeps Philadelphia mean solar time. This eventually expanded to the creation of universal time. And in universal time, the Earth is divided into 1 hour or 15 degree longitude. I guess we could call them wedges. They're not just a single longitude, they're like a longitude wedge, like a tangerine slice. And each time zone is synced with respect to the prime meridian. So universal time, UT, sometimes called Greenwich Mean Time, or GMT. By the way, if you're any military veterans here, I believe the military folks call it Zulu time, because Zulu is the nickname for the prime meridian, okay? This is the mean solar time of the prime meridian. So if anyone here is a BBC fan like I am, I don't know if Owen Bennett Jones is still one of the newscasters, but he had a cool voice, and I'd be driving home. He said, "It's 1300 hours GMT. This is Owen Bennett Jones at Bush House, London." And he's kind of broadcasting. If he's in London, which is pretty much at the prime meridian, Bush House, London is basically at the prime meridian. So if he's telling you 13 o'clock GMT, he's telling you it's 1 p.m. at the prime meridian. Now, we keep Eastern Standard Time. Eastern Standard Time is UT minus 5 hours. So we are 5 hours offset from the prime meridian. Why 5 hours? Well, do you guys remember what our longitude is? What's our longitude?
Of Rhode Island?
Yeah.
$42 north.
That's our latitude.
71.
Talking, pardon?
71 degrees west.
71 degrees west. Now, suppose you do 71 degrees. Let's do dimensional analysis. What's the conversion from degrees to hour? Give me numbers. I don't want you to have to think this every time.
Oh, it's 15 degrees in an hour.
So tell me what numbers to put top and bottom.
360 divided by 24.
Hell, I want the conversion factor. Fine, you could use that too. Give me a number for the top, give me a number for the bottom. You could use those two numbers if you wanted, but I think it would be smoother to use. I gave it to you in the previous page of notes. How many degrees per hour?
$15.
Right. So what number goes top and what number goes bottom, Nina?
1 over 15.
Right. 1 hour is equal to 15 degrees. Go ahead and divide those up for me. What do you get? 2 sig figs. Jeff, I hope you got a calculator. Oh, give me a frickin' break. Give me a frickin' break.
I am buying one for work.
Huh? Yeah.
I have mine at home. Yeah.
$8, dude. $8. You know how many of these things I have? I have like 20 of them. I stuff them in every crevice and crack and corner I can find.
Is it? It's 4.7
Units?
hours.
What's my point, Nina? Do I have a point? What's the point I'm trying to make?
I am lost. I'm not sure.
Does anyone see my point? My point is simply that's why Eastern Standard Time is 5 hours off from England. We're 5 hours behind England because 71 degrees translates to roughly 5 hours, right? By the way, look at that picture that I have here of universal time. Notice that it's not uniformly adopted by all places on Earth. Sometimes, like to keep everyone in the EU on the same time zone, they do a little wiggle around Iceland, probably for trade purposes, right? They do a little wiggle around some other spots. Look at China. China spans like 4 or 5 lines of latitude or hours of longitude. But China don't care. They keep one central time. I think they may have since adopted universal time, but I'm not sure about that. So sometimes for political reasons, people don't, but most other places do adopt universal time. Eastern Standard Time, Central Standard Time, Mountain Time, Pacific Time. There's also daylight savings time, which complicates things, but we'll save that for our labs today. We can use universal time plus the altitude of the stars to do celestial navigation. And that's the basis for one of our homework problems, chapter S147. Let's try that next. So let's start by taking this as a note. We can use, how do I want to put this here? Let's talk about celestial navigation. We can use the altitude of the sun or stars to give us our latitude. We can use a clock. Most ships will have a universal time clock. And if you compare it to local time, your local mean solar time, you can use that to get your longitude. And this is the basis for celestial navigation. We're going to try an example of that with a homework problem. So add this to today's homework. Chapter S147. Nina, why don't you read that off for us, if you don't mind?
Sure. Let me get it. Lost at Sea 1. During a vacation, you decide to take a solo boat trip. While contemplating the universe, you lose track of your location. Fortunately, you have some astronomical tables and instruments, as well as a universal time clock. You thereby put together the following description of your situation. It is the March equinox. The sun is on your meridian at altitude 75 degrees in the south. The universal time clock reads 2200 hours. Do you
So
want me
there
to?
are three givens. I want you to write them down. It's the spring equinox. The sun is at your meridian, or let's say the sun is on your meridian. And they gave us an altitude of 75 degrees. Did they give us the direction?
No. Oh, in the south.
So that's the azimuth. And the third thing they told us is that there is a universal time clock, and the universal time is 2200 hours. Let's start by writing down our givens. Next up, I want us to draw a little diagram of the situation. I'm going to remove this top note stuff, okay? So let's draw some waves because we're lost at sea. Let's put north on the right, south on the left. No matter where we are, we should have a zenith. So let's draw a boat. And let's draw our flag, our mast, the mast of our boat will be pointed up towards the zenith, okay? So here's your sailboat. We know the sun is on the meridian at 75 degrees in the south. So I'm going to use orange for the sun. Tell me where I should put the sun in this diagram. Tell me where to put the sun.
In between the zenith and the south, about 75 degrees.
Okay, so
Keep going. Nope, too far. Right there.
yeah. There's the sun. So that angle is 75 degrees. All right. Class, what should we do? What does question A ask, Nina?
Question A says, what is your latitude? How do you know?
Before I tell you how to do this, does anyone know the answer? Guys, what is the significance of the spring equinox? Why did they tell us it was the spring equinox? Why is that a given? What does that mean?
Is it to figure out the placement of the sun?
Correct. Now let's think about this. Where is the sun on the spring equinox?
It's at the celestial equator.
Very good. Here's a funny thing that you can say that's sort of true. On the spring equinox, the sun is on the spring equinox, okay? Do you see that? One refers to the day, the other refers to the point on the sky. On the spring equinox, the sun is on the spring equinox, but the most important part was already grasped by Nina. The real meaning of it is that the sun is on the celestial equator on that day. And that means in our diagram, not only is this the position of the sun, this is also the position of the celestial equator. How might that help me find my latitude?
Because 90 degrees from the celestial equator will give you north.
All right, that's true. That tells us that the north celestial pole should be 90 degrees from that. All right, that's one way to do this. So that tells me the north celestial pole is there. So keep going, Jeff.
So once we have our north celestial pole, we can figure out our longitude.
No, our latitude.
Latitude, I'm sorry.
Well, if you figure out the north celestial pole, you know Polaris, and so you can figure out your latitude from there.
Sounds good. Let's do it. What's the answer? You are 100% correct, Nina. Now I want you to do it.
Is the latitude 42 degrees?
Nope, you are not lost at the Rhode Island local C.
Oh, okay, we're doing, okay, yes.
You're lost somewhere else.
Yeah. Oh,
You have everything you need in this diagram.
75 degrees is the latitude?
No.
Oh, okay, I'm wrong.
The altitude of the celestial equator does not equal your latitude. I don't remember saying that.
Yeah.
Negative 20 degrees south.
No.
15.
15 degrees. All right, how did you get, now look, if this is 75, this angle here has got to be 15 degrees. Now there's two ways to look at this. The angle between the celestial equator and the zenith, we already decided was our latitude. But you can also see that 15 degrees is the altitude of Polaris. So our latitude is 90 degrees minus 75 is 15 degrees, but we're not finished yet. There are two 15-degree latitudes. Is this 15 degrees north or 15 degrees south?
North.
How do you know it's north, Nina?
Because it's above the equator.
How do you know it's above the equator? It is possible to go below the equator in a boat.
I am not sure.
Maybe it's time we took a look at what the sun's path looks like from the southern hemisphere. I have a slide for that. Jeff, do you have thoughts?
I was just gonna say, if it's on the equinox, it should be right at the equator, right?
No, it's the spring equinox. It's possible to go other places besides the equator on March 21st, right? For instance, I spent this March 21st in Rhode Island. And because of the pandemic, I suspect you did too. In the northern hemisphere, the sun, these are all backwards from our pictures, so I don't like this.
Are we getting the 90 degrees from the celestial equator to the north celestial point? Is that the 90 degrees?
Yeah, but you know, if we had been in the southern sky, the south celestial pole would be 90 degrees from the celestial equator.
Okay.
Let me see if I can do this using, I have pictures, but they reverse the direction of north and south. And I'm really worried that's going to confuse you guys because you already struggle with this as it is. So path of the sun, southern hemisphere. I'd like to find one where they didn't put north on the left. Only a weirdo puts north on the left. And since our book apparently was done by weirdos, look, more people putting north on the left. What the shit is wrong with these people? Okay. Here we go. Here's someone who isn't ridiculous. If you're in the northern hemisphere, like at 50 degrees north, from the northern hemisphere, the sun travels through this. Where do you put your plants? When you put the plants in one of your windows, most people put the plants in the southern window because the sun travels through the southern part of the sky, and that means your plants will get the most exposure to light, right? However, if you had a house in Argentina, you would not put your plants in the southern window because, now I need a picture from the southern hemisphere. I was thinking that there would have been someone out there that would have been cool enough to put north on the right. I can see now that everybody's copying the same diagrams, and that's really irritating me. All right, what I'm going to do, God damn it. All right, what I'm going to do is confuse you some more. I'm going to show you my slides. In the following slides, some foolish artist decided to put north on the left. And that's going to screw us up here, but I have no other options. Let's try to avoid this. If north is on the left, you can see the celestial equator and the sun travel through the southern part of the sky. If you go to the southern hemisphere, the situation is reversed. Now, the south celestial pole appears in your sky instead of the north celestial pole, and you can now see the celestial equator runs east to west through the northern sky. And that means the sun actually travels through the northern part of your sky. The reason you're supposed to know you're in the northern hemisphere is because the celestial equator is tilted towards the south. And that means if the celestial equator is in the south, you're looking at the north celestial pole there. If we had been in the southern hemisphere, they would have given the altitude of the sun as 75 degrees in the north. Does that make sense? All right. I took a little too much time on that. Then again, I am going to ask you a test question like this. Wink, wink, nudge, nudge, no secrets. So maybe you ought to think about that now. Okay, what's question B?
What is your longitude? How do you know?
Okay. To find the longitude, we're going to have to make use of this given. The universal time is 2200 hours. But even though they didn't tell you, there's a reason why you should know what time it is for that sailboat. What time is it in the sailboat world at the sailboat's longitude?
10. Well, is that what you're asking? I'm not sure.
I'm asking what time is it at the sailboat's position on Earth?
Oh, okay.
Something to do with the sun, guys. The sun is on the meridian.
This,
Noon?
That's right. If the sun is on the meridian, that tells you it's 12 noon local time for the sailboat because of the sun's position. It can't be midnight if the sun is up in your sky, right? To find your longitude, let's just first find the difference in time between you and the prime meridian. What's the time difference?
Ten hours?
That's right. 22 hours minus 12 hours. Ten hours behind England. How do we translate that into a longitude? You should already know.
15?
That's right. 10 hours, now you're getting there, times 15 degrees per hour gives us what?
150 degrees?
But we're still not done, are we, Jeff?
Nope.
Why aren't we done?
Because it's 150 degrees, which direction?
Right. Here we might want to make use of our experiential knowledge. Is Rhode Island east or west of England?
East.
Jesus Christ. Where's my shotgun? I want to go blow my brains out in the kitchen. Okay. We are.
Relative.
Huh?
It's relative.
Not if it's 71 degrees west. It's not. It's, yeah, relatively west, not relatively east. All right. Is England ahead or behind Rhode Island's clock? It's 1:30 p.m. Anyone have any friends in England? What time do you think
It's
it is?
ahead. It's ahead of us.
It's ahead of us. So let's see. We are behind England and England is ahead of us, right?
yes.
So what do you think, Kyle? Is this 150 degrees east or west?
West.
That's right. This is also behind England, or it's earlier than England, right?
Yep.
That's how I do it. If they had told me the universal time was like 600 hours, 0600, then we'd be east because we'd be ahead of England, all right? There's also a part C to this problem.
Yeah. Consult a map based on your position. Where is the nearest land? Which way should you sail to reach it?
We could do this with my globe, but let's try to do it with Google Maps or Google Earth. Okay. So let's search for 15 degrees north, 150 degrees west. I think, boom. Okay. Oh, wow, there's even a picture there. Ooh. That's where we are. What's the nearest land and what's the direction?
Hawaii
Which direction should we sail?
west.
northwest, right? So for part C, we should sail northwest to Hawaii. And that's the answer to S147.
I got
Okay,
a question.
yeah.
Would it be helpful at this point in time, just for like, you know, for the coming test, would like having a corner of my notes be like the 8-point compass be helpful? Like northwest, north, south, east, west.
I don't think there's going to be a ton of questions. I'll have one question out of 100, or maybe 2 questions out of 100 at Lost at Sea. So I think what's more helpful is to write down all of these notes and study them and practice them. Before the test happens, I'll probably devote one of our office hour sessions to doing practice problems for the test, because it seems like these practice problems are helpful. So we'll do a problem like this again. I'll change the numbers around and we'll see if you get it. The first time around, it's kind of like, whoa, holy shit, I've never done this before. So you might feel a little, dare I say, seasick. Okay. But hopefully, if you do it a second or a third time, it'll start to feel better. The other thing is you've got to learn your vocabulary terms. And that usually happens by writing them down, using them in these practice problems, and then slowly memorizing them, you know?
What's been helpful to me with the past is like going on Khan Academy and doing like math problems that are like the same thing that I'm learning in free time.
That is helpful if you have the time for it, but time is a precious commodity. Jeff's trying to squeeze this out while he's at work. Nicole's falling asleep because she's up with the kids all night. Time is a factor, right?
Yeah.
I've tried to build it in so that the practice problems we do in class, plus me beating up on you a little bit, should be enough training to awkwardly machete slash your way through the test. What I would recommend doing instead of doing Khan Academy is going back over your notes and resolving these problems at a later date. For instance, the way I would study for a test, and it took me a long time to learn this, is I would go back to Lost at Sea a month from now, and I would say, suppose that I would cover up the answer with a cue card. I wouldn't let myself look at it, because you're going to forget this in about 5 minutes, okay? I would cover this up with a cue card, and I would pretend that this was a test question, and I would see how far could I get before I start to choke. And then once I start to choke, I'd remove the cue card a bit and cheat. And that's how you'll actually learn. So instead of Khan Academy, I recommend Brendan Academy, okay? That's what we should be doing. Just a little more target focus to the problems at hand.
How
The
long?
test- Oh, Nina?
I was just asking how many questions were on a test.
100. It's going to be a big, awful thing. It's going to take you many hours to do it, okay? And all I can say now, Nina, is the homework questions we do will be excellent preparation for the test, okay? I'm not going to pull them out of left field. They're just going to be modifications of these. At this point, I think we should take a tea break because this is roughly tea break time, right? And when we come back, we've got more nutty stuff to do. I do need to try to work these problems into the second part of the lecture, and I will do that, okay? So let's give ourselves a good 25 minutes. I'm going to eat a New York bagel, which I'm very excited about. And after my New York bagel, we'll get back to work, okay?
So I'll see you in the lab.
Okay, yeah, you actually have to do some work here. That's fine, bud. Try to catch up on this later. Yeah, we'll start the lab right around 3 o'clock, okay? All right, I'll see you guys in a bit. Welcome back to the second part of our lecture. As I mentioned to the students offline a second ago, we're probably going to be doing a pre-recorded lab today, as I need to get some work done for the department by 5 p.m. today, and I need to get someone to the bus. And those things are kind of pushing up against the end of the day for me. Let's talk about some other stuff related to timekeeping. Some of this stuff is going to help you for your lab today, but I'm pretty sure that the recording that I have of eclipse prediction is pretty good. Would be nice to get to the moon at some point. Up to now, we focused on celestial navigation and keeping time by the sun. But it is possible, because of the difference of the solar and sidereal day, it's possible to keep time by the stars. So let's review some things that we learned about in our office hours. Okay, first order of business is there are two types of day. There is the solar day. The solar day is a true 24-hour day. It is sort of like the time for the sun to orbit the sky. If you guys remember that we start our day at the nadir meridian, to use a fancy term, it's the time for the sun to go from the nadir meridian up to the zenith meridian, and then back around to the nadir meridian. I only threw in the zenith meridian so you could distinguish the two. Contrast the solar day with the sidereal day. The sidereal day lasts 23 hours and 56 minutes. It is the time for a star, not the sun, a random star to orbit the sky. Here's the important thing about the sidereal day. The sidereal day is always a true 360-degree spin of Earth. Other side notes. Sidereus, is that right? It means star in Latin. So a sidereal day is a day with respect to the stars. And you guys remember sort of how the picture works. The reason for the difference is that Earth moves 1 degree along the ecliptic during a solar day. So if you want to look at the geometry of the situation, and I know you do, because I know everybody loves geometry, how could they not? If you wanted to look at the geometry of the situation, this isn't a great drawing. And now this is not drawn to scale, which is annoying. But it turns out that if this angle that the Earth moves is 1 degree, then by alternate interior angles in geometry, this angle here will also be 1 degree, something like that. So this is 1 degree, and therefore this is 1 degree. If the Earth is spinning and it rotates 1 degree, the Earth has to spin 1 more degree in order to point back to the sun. Now, it turns out that 1 degree is equal to about 4 minutes by dimensional analysis. you guys know that there are 15 degrees per 1 hour, right? So wait, how does this work? If the Earth moves 1 degree per day along the ecliptic, so let's see, 1 degree per day times, how do I not screw this up? 1 hour for every 15 degrees. So degrees cancel out. Wait, am I doing this right? $60 minutes. Wow, I am sleepy. 60 divided by 15. Yeah. You have 60 minutes per 1 hour. 60 minutes divided by 15 ends up giving you 4 minutes per day. That's kind of a weird screwball thing, that if the Earth is spinning, or the Earth moves 1 degree per day in its orbit, and 15 degrees is equal to 1 hour. This leads to a very funny joke in astronomy. You ready for the very funny joke?
May I ask a question first?
Yeah, sure.
When you say time for a star to orbit the sky, do you mean any star or like a specific star?
I mean any star.
Okay.
It turns out we're going to pick something different to keep sidereal time, but the star Vega, the star Arcturus, they all spin around the sky in 23 hours and 56 minutes.
Okay.
Okay? Here's a joke that astronomers make. The sun rises 4 minutes early each day. Now, this joke is so funny that it needs to be explained. The idea is that astronomers don't keep time by the sun. But that astronomers keep time by the stars. And this leads us to a new concept, the concept of what we call local sidereal time. Okay, let's take a look at this. This is the basis for one of our homework problems. We'll save 51 for last, actually. Okay, let's try this. Keeping time by the stars. There is a concept called local sidereal time, or LST. And local sidereal time has got a very confusing definition. Let me try it out on you. It is the hour angle. I'm going to abbreviate the term hour angle by HA. It's the hour angle of the spring equinox. I'll define hour angle in a second. This for now won't mean anything to you. The idea is that you keep time by the movement of the spring equinox, and I'm talking about the point on the sky in Pisces. You keep time by the movement of the spring equinox across the sky. In a weird twist, the sidereal day starts when the spring equinox crosses the zenith meridian. This is one of the things that's going to be confusing about sidereal time. We're so used to midnight being the start of the day when the sun is like below us. But now we're going to be starting time at noon-ish when the spring equinox crosses the zenith meridian. Okay, and then it goes from 0-100 hours. Now, how long should it take the spring equinox to rotate around the sky? Take a guess. How many hours and minutes will it take the spring equinox to rotate around the sky? I'd like to remind you guys that the spring equinox is a point on the local sky, right? There you go. Every day, this little empty spot on your sky rises and sets. How long should it take for it to orbit the entire sky? This is
23 hours
just 23 hours?
and 56 minutes.
That's right. So a sidereal day, we already discovered, is 23 hours and 56 minutes. So Nina, this is where it gets confusing. If we kept sidereal time in 23 hours and 56 minutes, the increments of hours and minutes would be kind of awkward to keep track of. So what astronomers do is they cheat. And even though the spring equinox should orbit like any other star, 2356, they redefine the hour so that there's a 24-hour clock for sidereal time. Yes, that's a little awkward, but it's even more awkward to keep track of days that iterate every 23 hours and 56 minutes, okay?
Basically just rounding up.
Something like that. Basically, yes. They're letting the length of an hour smudge a little bit. I need to define hour angle for you. Hour angle means something really simple. Time since the meridian. How many hours since the object crossed your meridian? I also am going to eventually relate local sidereal time and hour angle to our definition of right ascension. Right ascension we studied last class. I'm going to give you a quick and dirty definition of right ascension. It's hours east of the spring equinox. These three quantities, the local sidereal time, the hour angle, and the right ascension, are related to each other by a famous equation, which I will explain in a moment. The hour angle of a star is equal to the local sidereal time minus the right ascension. This is a famous formula that kind of defines local sidereal time. I have a little nickname or a mnemonic device for it. I call it Ha equals list minus raw. That's how I remember it. Ha equals list minus raw. It's goofy, but it works. Okay. I'm guessing that all of this stuff makes 0% sense to all of you, and that's understandable. It's very confusing. Why don't we draw a picture of the local sky and let's see it visually? I think that'll help. But I wanted to start by just plopping the definitions down just so they're there, okay? Can I erase this, three friends? I guess I'll take that as a big fat yes. Okay. How to do local sidereal time problems. The first issue is you got to draw a effing diagram. This is the single most important piece of advice you'll get from me all semester. Draw an effing diagram. This time, we need to draw a diagram that is east to west. And we want to put east on the left and west on the right. I'll explain why. Start by leaving yourself some headroom. And once again, we're going to make another one of those two-dimensional drawings. You could make yours about, I don't know, 10 centimeters. Put a mark at 5 centimeters. And then let's use our technique of using the radius, half the line, to draw in a few points. Then we can draw in a snazzy dome that does not suck. Unlike our other drawings where we went north to south, this one is going to go east to west. The observer stands in the middle. This is the ground. Now watch this tricky maneuver. Usually when we draw the line through the observer, that line represents the observer's zenith. But here it's more complex than that. This line doesn't represent the zenith as much as it does the observer's meridian. And the simple reason is that not all stars pass through your zenith. For instance, if you look at the diagram that I showed you earlier of those star tracks, wherever they are, okay, if your star happened to be located at a declination of positive 42 degrees, then fine. Maybe that star would come up and at its highest point in the sky, it would cross your zenith and it would come back down. But not all stars have a declination of positive 42 degrees. Most stars will be located at some other random point on the sky, like here at this blue ring, which we decided was like positive 30 degrees. That star will rise in the east. It won't cross your zenith, but it will cross the meridian at the highest point, and then it will set in the west. Our two-dimensional drawing represents the path of a random star. We know it will cross the meridian in general, so that's why this is our high point, because we're going east to west, okay? Let's start off slow and simple. Let me make a blue star, and let me put that blue star about 15 degrees off from the meridian in the western direction. I wonder how I did with that angle there. I have a big protractor somewhere. I've been kicking this around the apartment now for days and weeks. Well, I guess I could use a normal protractor too. Let's see how I did. Hey, that's pretty good. That's just about 15 degrees. I'm good at this stuff, apparently. Okay. How long ago was that star on my meridian? If this is 15 degrees, how long ago did that star cross my meridian?
An hour ago?
That's right. So we would say that the hour angle of that star was 1 hour or 100 hours. Because that star crossed 1 hour ago. That's what we mean by hour angle. Hour angle is the position of a star. Instead of measuring it in degrees, we're measuring it in hours because the star is constantly rotating. Okay, let's say that the spring equinox is going to be represented by the green X, okay? And let's see here. The spring equinox is in the constellation Pisces. Let me just place it at a random location on the sky for illustration purposes. Let's say at this particular moment that we're doing in our example, the spring equinox was located roughly over here. What would you say the hour angle of the spring equinox was, Nicole? Take a guess.
I'm just gonna take a wild guess and say 6.
Well, hold on. How many hours is it around the sky?
Roughly 24.
Roughly 24. So how many hours is it to get to the western horizon?
12?
No, if it's 24 around the clock, then 12 hours would be down here, right?
Mm-hmm.
How many hours would it take to get to the western horizon?
6.
6. So that can't be 6 because 6 would be a quarter turn around
Okay.
the sky. Do you agree with me that 6 hours is 1/4 of 24? Then from here to here is 6 hours. Now give me a more reasonable guess for the spring equinox.
4.
Okay, fine. You have just identified the local sidereal time. The local sidereal time is 4 hours because we defined the local sidereal time as the hour angle of the spring equinox. Okay? So if you're keeping track of a random star, it's hour angle. If you're keeping track of the spring equinox, it's the local sidereal time. Let's regurgitate the definition of right ascension. From your previous page of notes, how did we define right ascension?
Hours east of spring equinox.
In which direction is east on the sky?
Oh, counterclockwise.
So the right ascension then should be start at the spring equinox and drift back eastward towards the star, or just drift in the eastward direction. You can tell this is east because that's where we go. Okay, what is the right ascension of the blue star in my current setup?
From the spring. Oh wait, yes, from the spring equinox.
How many hours from there to there?
4. No.
False.
3.
That's right. How did you know it was 3 hours?
Because the star is an hour away from the meridian, and the spring equinox is 4 hours away. So
Good. And this is what we mean when we say ha equals list minus raw, right?
Yeah.
A star with an hour angle of whatever will always have that relationship to the local sidereal time and to the right ascension. Now, this turns out to be really confusing to learn, but it turns out to be really helpful at an observatory because oftentimes you want to pick a star like Vega, and if you're trying to observe Vega, you want to know how many hours until it's up. Obviously, a star is best observed when it's at the meridian because it's as high as possible in the sky. You don't want to look at a star when it's along the horizon. One, there's trees and buildings in the way. Two, you're looking through a longer column of atmosphere, so there's more water vapor and light pollution. Stars just look better when they're high in the sky, and they look like shit when they're on the horizon. Oftentimes, you want to know how many hours until that star will be best observed. You can solve many different problems using local sidereal time. I have a couple of made-up examples, but one of our jobs was to do 53 ABC, and that's a nice application of this. So let's leave this diagram up for a moment because I think it's going to help. And let's have Kyle read us question 53, if he's willing.
Yeah.
Actually, you know what? I apologize. I need too much board. Do you guys have this down? I need to erase this, okay? We'll draw another quick diagram. Okay, back to homework number 3. Homework number 2. And this is question chapter S1, 53. I'm going to skip over 51 for now. Go ahead and read me 53. Or what's the title and everything, Kyle?
What? The title?
Yeah.
My papers are all disorganized. I have in front of me eclipse predicted, and then the other one I have
Wait.
is
Kyle, all right, can someone else read me the question? Look, Kyle, in the future, here's what you do. All you got to do to read me those questions is you click on the chapter 3 PDF and you open it up and boom. The title, right?
That's all.
Yeah. The title of this problem is Ha equals list minus Ra. Okay. Can Nina or someone read this for me instead?
Yeah.
sure. So it says our angle equals local, is it sidereal? How do you pronounce that word?
Sidereal.
Local sidereal time minus right ascension. And then it says A, it is 4 p.m. on the March equinox. What is the local sidereal? Oh, I keep forgetting how to pronounce it. I'm sorry. Sidereal time?
What's the local sidereal time?
Sidereal. Okay.
Sidereal.
Sidereal. Okay.
When you solve these problems, you got to draw a diagram. I'm going to draw a quicker diagram, okay? So I'll draw a quick little dude. Mark the midpoint. I'm going to be fast and sloppy this time. Not bad for freehand. Remember, this is the meridian. This is east, and this is west. Let's start off with the givens. It's 4 p.m. in the March equinox. What does 4 p.m. tell us? Does anyone know what AM and PM stand for? No? No one knows what PM stands for?
Well, 4 p.m. would be in the evening. obviously.
What? So, I'm sorry, say that again, Nina?
I was just going to say 4 p.m. would be in the evening, so it would be past the meridian.
That's what PM means, by the way. It means post-meridian. But what is it, Nina? What is past the meridian?
Oh, the star.
Uh-uh.
The
4 p.m. is not sidereal time.
So the sun.
That's right. When you keep solar time, 4 p.m. means the sun is 4 hours past the meridian. AM means anti-meridian or before the meridian, right?
Okay.
Okay. So tell me where to draw the sun.
So the sun would be in the west.
Yep.
Like,
Let's see. This is 6 hours, right?
yeah.
So
So
half is 3.
a little past half down.
Yeah. Probably like there, right?
Yeah.
That's what they're telling us. They're telling us the sun is 4 hours. Basically, you know, when they tell you it's 4 p.m., that's the hour angle of the sun. They're telling you how many hours since the sun crossed the meridian. Okay, how the shit is that going to help us figure out local sidereal time? Local sidereal time keeps track of what?
The hour angle of the spring equinox.
Very good. The hour angle of the spring equinox. But oh crap! They gave me the hour angle of the sun. So how am I supposed to figure out the hour angle of the spring equinox based on the hour angle of the sun? Any thoughts on that one?
Was the sun on the spring equinox? So they would be the same, right?
Right, because remember, on the spring equinox, the sun is on the spring equinox, right? On the day of the spring equinox, the sun is at the point, meaning the spring equinox is there. So what's the answer to our question?
Sorry, I forgot what the question was.
Me too.
It says it is 4 p.m. on the March equinox. What is the local sidereal time?
So what is the local sidereal time?
4 p.m.
We don't use PM. in
For
si-
400. Yeah, 400
Yep.
hours.
4 hours or 400 hours if you speak like military people. So here's how we just did this. The local sidereal time is 400 hours. In physics and math and in astronomy, when you use a diagram to solve a problem, you say by inspection. By inspection means I drew a diagram and I looked at it and that's how I figured it out. Okay?
Yes.
Very cool. Remember how I told you before that the fact that the spring equinox means so many things? That you could be asked tricky questions like, what's the location of the spring equinox at noon on the spring equinox? Do you think you could answer that question now? What is the location of the spring equinox at noon on the spring equinox? What's the answer to that riddle?
On the meridian?
Very good. Now you have achieved learning, and I am impressed. You could not have answered that question a week ago. All right, B. What's B asked of us?
B says the local sidereal time is 7:30 or no 19:30. When will Vega cross your meridian?
Now, I'm going to help you out here. We can look up the right ascension of Vega. The book gives it as 18 hours and 35 minutes, but the book's using some out-of-date coordinates. Maybe we should try to do Vega star. According to Wikipedia, which probably has the most recent coordinates, oh, 18 hours and 37 minutes. What do I want to do? Do I want to make this hard? Maybe I should make this hard for me. The right ascension of Vega is 18 hours and 37 minutes. For stuff like this, guys, we just use the formula. Ha equals list minus Ra. So we have to solve for, oh, what was the question again?
The question is, the local sidereal time is 1930. Am I pronouncing that right? Like saying that 1930, is that right to say?
Yeah, that's great.
When will Vega cross your meridian?
When will Vega cross next? Okay, let's set it up over here. Whenever I do Ha equals list minus Ra, I like to stack them vertically. That's because we've got to keep our hours and minutes separate. So the local sidereal time is 1930. And we're going to subtract that from 1837. Do you guys know how to subtract this?
It would be like 153. Is that right?
Almost.
0.93.
Pardon, Jeff?
0.93.
Or Joey, whoever that is? Oh, no. No.
That's me, yeah.
Whoa.
Whoa.
Time is not decimal based. It is.
Oh, wait, no.
Joey, sorry, I'm talking to Joey. Time is sexagesimal based, right?
What?
Joey, I'm worried that you did some kooky thing like this. You can't do 19.3 minus 18.37. That don't make no sense because that's out of 100. But the hour iterates every 60 minutes.
I think you're, yeah.
Hey, you know that song? Gotta keep them separated. For hours and minutes, gotta keep them separated. You can't mix those two things up. Let me show you my way of doing this. I keep them separated. I just coldly subtract the minutes. I coldly subtract the hours, and then I try to glue them back together. So if I were doing this, I would do 30 minus 37 is -7 minutes. 19 minus 18 is +1 hour. So now you take 1 hour and you subtract 7 minutes. And what does that give you?
53.
That gives you 53 minutes. But I will remind you that 53 minutes is the hour angle. What is the definition of hour angle, Nina?
Is the time since the meridian.
Time since the meridian. But what did the question ask?
When will Vega cross the meridian next?
So if this is 53 minutes ago, when will it cross next?
Wait, so has Vega it has already crossed the meridian?
Yeah, so it's like over here. It's approximately 1 hour past the meridian.
Okay. So it's going to cross again in like 22 hours.
Use a 24-hour clock for sidereal time. Cheat.
23
And
hours in like 7 minutes?
yeah, I think so. So we do 24 hours minus 53 minutes. Here's another trick. If you borrow an hour, you could subtract 60 minus 53 because 60 minutes are in an hour.
Yeah.
And that, so 23 hours and 7 minutes. And that's the answer to our problem.
Okay.
Tricksy stuff, I know. Just remember, Joey, Keep them hours and minutes separated. Okay, let's do part C, and then we'll put this puppy to bed. Oof, I think I have just enough time to do the final problem too. What's part C ask?
Part C says, you observe a star that has an hour angle of 13 hours when the local sidereal time is 8:15. What is the star's right ascension?
We're gonna have to rearrange ha equals list minus raw. Does anyone have the algebra chops to do that? How do you solve for right ascension?
Would it be local sidereal time minus hour angle?
Good. Yeah, because I would add RA to both sides, and then I would subtract hour angle from both sides. So raw is list minus ha. Very good. Okay. That means we've got to do 8:15 minus 13 hours. How do you guys want to try to do this? You want to try to use my method, or you want to use your own method? Well, you can't plug it into a calculator, really. Well, I mean, you kind of can. Who can do this?
Is it negative 5:15 plus positive 15?
There you go. -5 hours. I like you using my methods. Nina, you're good. Positive 15 minutes. Okay, now take -5 and add 15 minutes positive. What do you end up with?
Wait, repeat that.
If you have -5 hours and you add positive 15 minutes, what do you have?
10. No, -10. Positive 10. I can't do the math in my head.
This is 15 minutes. That's -5 hours. Let's think about it on a number line. Here's 0.
I think I know, but I don't know. I mean, I do know, but I don't want to like interrupt.
I want you to interrupt. It's a team effort, Kyle. Takes a bit.
I think it would be -04 with the 2 dots, and it would be +45.
Damn, he's good. Or no, -445 all at once. Because look at a number line. If you're at -5 hours and you add back 15 minutes, you're now at -445, right? Do you see what I mean on a number line there? Very good, Kyle. This is equal to -445, where like the negative is included with the whole thing. However, this is a right ascension. That's a little bit awkward because right ascensions are normally not negative, they're positive. How do we define right ascension? I'm going to erase this bottom part.
Right ascension is hours east of the spring equinox.
So what does it mean if we have a negative right ascension? If right ascension is hours east of the spring equinox.
Are we going west?
That's right, but that's a little uncool because normally we don't mess with west right ascensions. So we need to convert this back to an eastern or positive right ascension. How should we do that, Nina?
I'm not sure.
Well, if this is the spring equinox, -4 hours means we go like that.
Yeah.
But we want to convert it back to a positive eastern. How many hours around the clock is 24? So we do 24 hours minus 445. And now we're subtracting both the minutes and the hours.
Would you times it by 2 and add it to itself to get
Maybe,
it?
but here's how I would do it. I would make this 23 hours and 60 minutes minus 445. What's 23 minus 4?
19,
What's 60 minus 45?
15.
And that's your answer.
Wait, why
Oh.
2360?
Because isn't 24 hours the same thing as 23 hours and 60 minutes?
Oh, yeah.
I just didn't feel like doing 0 hours minus, I didn't feel like doing 0 minutes minus 45. Do you see that trick? I borrowed an hour from 24 and I put 60 cents in. You know, it's kind of like when you make change for $1.
Okay. Can you briefly go over how you got the negative 445 again?
Sure.
Yeah, thank you.
This was negative 5 hours, but positive 15 minutes. You've got to take minus 5 hours and add 15 back on it, right?
Okay.
So let's use the number line. Let's assume this is 0, negative 1 hours, negative 2 hours, negative 3 hours, negative 4 hours, and that's negative 5. If that's negative 5 hours, but then you add 15 minutes, you've got to drag back a quarter of an hour towards 4. That ends up being negative 445, something like that, right?
Yeah.
Okay.
Okay.
That was how I thought about it. I suspect that's how Kyle thought about it too.
Okay.
Yeah, I was thinking about it the wrong way. I was like thinking of it like basic math instead of the 24-hour scale. I was like, oh, do I just times it by 2 and add it, the previous number, the 445, so that it's positive in the same number? I was thinking of it like that earlier. I completely forgot about the 24 hours.
Right. I'm going to erase all this. So I've got a few minutes left before I turn you over to the lab. And I'm going to be doing a pre-recorded lab because I have some of my own work to do and I've got to get Jordan to the bus. But let me make a deal with you. Our lab today is on eclipse predictions. This problem is about planetary calculations. What I'm going to do to help you maximally on the lab is let's get rid of question 51. So today's homework will just be the 4 questions that you turned in. I think we did this once before, right? And it worked out okay. So first thing I'm going to do before I forget, in case people are doing the homework with a previous one, we're going to take homework 2. What? Fucking hate Blackboard. Okay. We're going to take homework 2. This is just before I forget. And we're going to just delete question 51. Normally I like to do 5 questions, but it just wasn't in the cards because we're a little behind. That not doing a homework next time will fix this. 51 omitted. All right, that solves one problem for us, okay? Now, instead of taking the last few minutes trying to solve that problem with you, I can do something different, which is talk to you a little bit about eclipses, which is the basis of our lab today. Okay. Our final module today will be on eclipses and phases of the moon, okay? So I'll probably go over this again next class, but let's start by drawing a little picture of phases of the moon. The Earth, as you saw in your lecture, is a big, giant spinning clock. And let's go ahead and show you, see if I can get this slideshow up here. Okay. Function F582. The Earth is a big spinning clock. When your head points towards the sun, that's 12 noon. When your head points away from the sun, that's midnight, 6 a.m. and 6 p.m. as the Earth rotates. The moon takes roughly a month to orbit around Earth. And what we're going to do is we're going to define the phases of the moon in terms of these 8 positions. So I want us to kind of quickly draw a picture like this. Let's quickly learn about our phases of the moon. Start by drawing a circle that represents Earth in the center of the page. And in order to do this, we have to specify the direction of the sun. So the sunlight is going to be the sun is way off to the right. And that means we can draw in what we call the terminator. The terminator is the boundary between the daytime and the nighttime side of Earth. Obviously, the side facing the sun is day. The side away from the sun is night. The Earth is a spinning clock. 12 p.m., 12 a.m. Which direction does Earth spin as seen from north?
Counterclockwise.
That means it's spinning like this. So from 12 p.m. you go to 6 p.m. and 6 a.m. You can even throw in 3 o'clock and 9 o'clock if you want to. Let's draw in 8 moons. 1, 2, 3, 4, 5, 6, 7, 8. It helps if you can make them circular, but I'm doing a crap job. Actually, even though they'll be a little big, maybe I'll use the circles here. I've got motivation to do that. Just hear me out. I don't think we can ever use these breadcrumbs again. It's going to be covered in a dry erase marker. Okay. Draw in the terminator for every single moon. The terminator should be in the same direction as Earth's terminator. The illuminated part of the moon should face the sun. The dark side should face away from the sun.
Can you just repeat
This is what the phases of the moon look like from outer space. It is not what the phases of the moon look like from the ground. You've spent your whole life on the ground, unless your name is Buzz Aldrin or something. So you haven't seen this perspective before. Let's shade in the dark sides of the moon. Okay, first the names. The moon that's between Earth and Sun is the new moon. The moon that's on the opposite side of the sun is the full moon. The moon also orbits counterclockwise. So the moon is growing in your sky as it goes from new to full. This growing is called waxing. This moon is a waxing crescent. This moon is called first quarter. This moon is called waxing gibbous. As the moon goes from full to new, it will shrink. This moon, shrinking is waning. This is the waning gibbous moon. This is the third quarter moon. And this is the waning crescent moon. The reason why the moon takes different shapes or phases in the sky is because when you look at the moon from your position on Earth, you only see a two-dimensional cross section. For instance, if it was new moon and you were standing on Earth such that it was 12 p.m., the sun's above you in the sky, you're looking at half of the moon that's enshrouded in darkness, and you're seeing it during the day. In other words, you don't see the moon at new moon because it's up during the day and only the unilluminated side faces you. So for new moon, you don't see anything. On the waxing crescent moon, on the other hand, you're looking from about 3 p.m. in that direction. And that means you're going to see a cross section of the moon that looks something like this. In a two-dimensional drawing, that might look like a slice of pizza. But remember, the moon is a three-dimensional object. That slice is a tangerine wedge. And when that tangerine wedge is flattened, the fact that the moon has a three-dimensional belly means that the waxing crescent moon, it looks like what they say in the Arabian Nights, they call it the fingernail moon, right? It looks like a fingernail. That's a waxing crescent. At a first quarter moon, you're seeing a cross section from that direction. You see half of the disk illuminated. So for the first quarter moon, you're going to see a perfect half disk, although it's only a quarter of the moon's surface, right? The gibbous one is kind of strange. For a gibbous moon, you're looking in this direction. So now you're seeing, well, I didn't draw that very good. Ah, shit. I just did the same thing. You're basically seeing a pizza wedge in darkness, and you're seeing a chunk of the moon minus this little fingernail. The result is that the gibbous moon kind of looks a little bit like an egg. It's round on one side, and it's sort of got a missing pizza wedge on the other side. So the gibbous moon kind of looks egg-shaped. And then it repeats itself. Waning gibbous is egg-shaped, half a disc, fingernail-shaped, nothing, okay? Using this diagram, you can also figure out what time the various phases of the moon rise and set. For instance, remember that if your head or your meridian points towards the blue arrow, as Earth spins, these moons will rise and set above your horizon, this being your eastern horizon and that being your western horizon. So the new moon, for instance, the new moon will cross your meridian at 12 p.m. But as you spin, the new moon will set at 6 p.m. And that also means the new moon will rise at 6 a.m. So add this note. The new moon will rise at 6 a.m., cross your meridian at 12 p.m., and it will set at 6 p.m. In other words, the new moon is up all day. Okay, you guys try it. How about the full moon? What time will the full moon rise?
6 p.m.
That's right. Because when your head spins to 6 p.m., the full moon will come above your horizon. All right, keep going. What time will it cross your meridian?
12 a.m.
What time will it set?
6 a.m.
The full moon is up all night. One more, Nina.
Okay.
It's 3 a.m. and you're drunk and
Okay.
you're stumbling out of the bar after hours. You look to the east and you see a crescent moon on the horizon. Is it a waxing crescent or a waning crescent?
It's 3 a.m.
Yeah.
It's a waning crescent.
Very good. Because if your meridian is pointing in the direction of 3 a.m., only the waning crescent moon could be coming up above your horizon. The waxing crescent moon you see around dinner time at 6 p.m. The waning crescent moon you see if you've been up too late, or rather up too early, depending on how you look at it.
Yeah.
I got one more mini module. I went a little over time budget today, so forgive me. It kind of looks like you should have an eclipse every time there's a full moon or a new moon, but you don't. And the reason why is that the moon's orbit is not inside the plane of the ecliptic. As you can see from this picture, the moon's orbit is inclined by about 5 degrees with respect to the ecliptic. It plunges above and below the plane of the ecliptic. So oftentimes when you have a new moon, yeah, the new moon is in between Earth and the sun, but it's actually a little bit below or sometimes above the ecliptic plane. This is why you don't always have an eclipse during new moon. Likewise, you don't always have a lunar eclipse because during full moon, the moon might be 5 degrees above or below the plane of the ecliptic. Sometimes, however, you do get eclipses. And in today's lab, you're going to be hunting for eclipses. Usually at 2 points during the year, as the moon is orbiting around the Earth and the Earth is orbiting around the sun, the whole thing will line up in a certain way where the moon will cross the ecliptic plane right around either new or full moon. And that's when you get eclipses. There are 2 eclipse seasons every year. We actually just had a lunar eclipse, what was it, last week, but we were not really in the right place to see it. We don't have a lot of time. You have to start your lab, but you're going to need the following information for lab. It's also notes that I want to give you. So just let me put them down on the board quick and sloppy, okay? I'll erase all this. Okay. This is needed for your lab today. There are 2 conditions for an eclipse. The first condition is the phase of the moon has to be either new or full. If the phase of the moon is new, you will get a solar eclipse because you'll block the sun. If the phase of the moon is full, you'll get a lunar eclipse because the moon is blocked by Earth. Or rather, Earth blocks the sunlight from falling onto the moon. The second condition is that the moon must be at a so-called node. A node is a term that means the moon is crossing the ecliptic plane. It turns out that there's 6 types of eclipses. And the reason why there's 6 types of eclipses is that astronomical objects, I forgot about that. That's kind of neat. An astronomical object casts two types of shadows in space. There's a penumbral shadow, which is a partial shadow. The penumbra is a partial shadow because rays from the top of the sun can penetrate that part. Rays from the bottom of the sun can penetrate that part. There's also a much darker umbral shadow. That's a complete shadow. No rays that leave the sun can actually penetrate behind the Earth in that cone. So that makes a kind of partial shadow and a total shadow. Take those as notes. Two types of shadow. A penumbra is a partial shadow. Umbra is a total shadow. Now, I can talk about eclipses more next time because I'm like wicked out of time. But the last thing I'm going to have you do is I'm going to label the 6 types of eclipses so that you can do your labs today. And then I'm going to turn it over to pre-recorded me because I got a lot of crap to do today. All right. You guys have all this? Notes taken? All right. I'm going to give you the link in the exact timestamp. Just give me a second. Our very last note of the day is that there are 6 types of eclipse. And next time I can talk about them with a little more detail. There are 3 solar eclipses and 3 lunar eclipses. The difference between the types of eclipses have to do with whether the moon or the Earth enter the different types of shadow. For instance, you'll be able to see the 3 types of eclipses that the moon can make. I'll use yellow for the moon. Because the moon can either be, let me small this a little bit. Okay. The moon can be in the penumbra, which is a penumbral eclipse. The moon can be inside the umbra, which is a total eclipse, or the moon can be sort of half and half. That's a partial eclipse. And there's a similar sort of logic for the sun too. So for the lunar eclipse, we have penumbral lunar eclipse, a partial lunar eclipse, or a total lunar eclipse. For the solar eclipses, you can have a partial solar eclipse, you can have a total solar eclipse, and then you have that annular solar eclipse. That's when the sun does not get completely blocked. As you will discover in your lab today, the annular solar eclipse happens if the eclipse happens within 8 days of apogee. Do you guys remember what that term means? Apogee? What the hell is apogee? Well, I'll leave it to the reader and exercise the reader to discover what apogee is. Maybe you'll find out in your lab today. Okay. I need to farm out the lab today because I've got several things to do before 5 o'clock or I'm screwed, and I only have like an hour and 40 minutes to do it. Now, you guys promise if I give you this recording, you're not going to screw off. You're going to watch it and you're going to do your lab just like normal, right? Okay, you've got to do this. It's due. So let me find you the link and I'll give you the exact timestamp. Just a moment here. Let's go to our announcements section. I kind of want you to see how I do this in case you have to do this. This is lab number 3. So let's hunt back. I think one of them I did a really nice job of it. I think so anyways. I remember I think last semester it went pretty well. So let's go to AS1010 lecture 3, homework 3, lab 4. Ooh.
Do you post the grades on Blackboard, or will we see them at a
I did grade your papers and the grades are there, but Blackboard tries to take all these averages of things without thinking about how my rubric works. And I didn't feel like plugging them in. So I will post the grades at some point. You can see whether you've done a homework or missed a homework, but you can keep track of your own labs and your own homeworks by saying, well, how many did I turn in and how many did I miss?
Yeah, I just couldn't find grades on the thing, so I was just wondering.
Couldn't get my mic to work. Apogee, the highest point in the orbit, furthest part away.
It's the furthest part in the orbit from Earth. Very good.
All
You
of my
could say
orbital
it's-
mechanics comes from Kerbal Space Program, so you gotta deal with me.
No, that's cool. That's a plenty good way to learn that stuff. So it's interesting that you said the highest point in orbit. There's a certain logic to that, but I would say the farthest point in orbit. Okay. Okay. So this URL here has lab 3. Let's see if I can find it. Maybe I can even, there's a way to link you guys to the timestamp. Good morning. These are the guys in last semester's lecture. All right, here we go. That's about where it starts. I have some, there you can see we're doing perigee and apogee. Okay. So that's probably a good place to start, 137. Can I copy this? Copy video URL at current time. How cool is that? Timestamp 137:12. Chat. Blech. I just want to write this down before I forget it. Now I think if we click this, it should open up to that exact moment because that's how I tried to do it. Yeah, how dope is that? Okay, so there you go. Now, and as always, the first thing we'd like to do is let me tell you where you're going to get this. For your lab today, go to lab 3, eclipse prediction, and this is what you're going to want to print. I'm not going to waste the printer ink since I'll be doing it. Honestly, all you really need for today's lab is you can even follow me on the data table or you can read it on your computer. This is the page you really need here, 4-5, and that's the 5th page. So when you hit print, go to custom and just print page 5. That's all you're going to need if you're doing a printer. That's the data sheet, okay? You might even be able to fill it out on a PDF and turn it in that way. You've got lots of options.
So this week, what we're handing in is homework 2, lab 3, lab 4.
That's correct. Does that make sense?
Yes.
And you're going to do lab 4 with past me so that present me can get his work done for a change.
Lab 3.
Huh?
Lab 3.
Yeah, I'm sorry. Did I say something funny?
Lab 4. I just wanted to clarify.
Yeah, lab. Well, on Friday, we'll be doing lab 4, but today we're doing lab 3. Yep. Okay. Okay, guys, sorry I have to abandon you, but I got my own damn work to do, and it's serious today, okay? If I had time to kill, I would, but I don't. So I will see you guys on Friday. Remember, Friday class will start at noon because I have generously given us the day off from homework. That ought to reduce the crap we have to deal with on Friday. That's nice. We will squeeze out a little lab, no big deal. I'll see you guys Friday at noon, okay? Please get that lab done now before you forget and turn it in. Okay, take care. See you Friday.